If Mars once cradled rivers, lakes, and a breathable sky, if its valleys once hummed with the slow, patient chemistry of life, then a simple, disquieting question arises and refuses to leave. What, if anything, might have grown in that vanished wetness? What forms of mind, if any, could have looked back at their red horizon and wondered the same thing about their small, temporary place in an immense universe? The question is startling because it pulls two very different kinds of thinking together: the sober arithmetic of planetary science and the wild human tendency to imagine histories erased by time. It is a question that feels almost illicit in its scope, because to ask it is to admit that the past need not be unambiguously benevolent evidence. It may be riddled with absences that are not merely empty but deliberate erasures by the slow, indifferent processes of deep time. This opening question lands like a stone in a quiet pond. The ripples spread outward. For some, the ripples are wonder, a childlike reaching toward possibility. For others, the ripples are caution, an insistence that the scientific method requires evidence, not fantasies. For everyone, the ripples arrive with a particular taste, the taste of smallness. Humanity has spent centuries convincing itself that it can understand the past, read its strata and bones and scars, and reconstruct with some fidelity the sweep of geology and biology. Yet even as humans map continents and sequence genomes, the red planet offers a counterexample, a place where time has been both preservative and destructive in ways that complicate any simple narrative. To frame the question more carefully is to recognize that it is not merely fanciful, it is numerical. It asks, in effect, given what is known about Mars, its age, its climate history, the amount of water it may once have held, the intensity of its early bombardments, the flux of solar energy across its surface, how plausible is it that conditions suitable for complex life and, even more tentatively, for technologically capable life could have existed there long enough for such trajectories to develop? The question collapses into a handful of measurable parameters. Those parameters do not answer the question, but they shape it. They constrain imagination with scales and probabilities. They are the scaffolding for any careful speculation. 1. Age in temporal windows. The solar system has an age, roughly 56 billion years. Mars formed early in that timeline and carried its surface story from the beginning, recording epochs of heavy impacts and gradual cooling. The planet's ancient valley networks, the fracture patterns, and the mineralogical fingerprints of clays and sulfates suggest that liquid water was once stable on the surface. Many models place the epoch of widespread surface water between about 1 and 3.5 billion years ago. That means there may have been a window hundreds of millions of years long, perhaps more, when standing bodies of water, flowing channels, and a thicker air were possible. Put numerically, a span of 500 million to a billion years is non-trivial. It is, in earthly terms, enough time for microbial ecosystems to emerge and diversify, and for complex multicellularity to begin its slow ascent. But timing alone is not destiny. On Earth, life's earliest signs appear very early, within a few 100 million years of planetary stabilization. Yet complex life required billions of years of cumulative processes, oxygenation events, stable climate regimes, ecological feedbacks. The comparison is sobering. If Mars's hospitable period was truncated or episodic, the time available to reach anything resembling Earth-like complexity would have been compressed. Still, numerical possibility is not the same as numerical probability. A 500 million years might be short to generate a technological civilization by Earth's pattern, but it may not preclude other pathways, faster evolutionary jumps, different biochemistries, or social structures that emerge under pressures not familiar to terrestrial history. 2. Water volume and distribution. Liquid water is the sine qua non for the story. Paleodeltas, shorelines mapped by orbital probes and hydrated minerals point to significant volumes at certain times. The amounts are debated. Models suggest anything from transient lakes and rivers to ocean-scale bodies that could have covered large basins. Numbers here are both specific and slippery. An ocean covering the northern lowlands would have been thousands of kilometers across, a shelf of water deep enough to produce stable shorelines. Even more constrained, water-connected lakes and aquifers would change planetary dynamics, weather systems, erosion rates, and the potential for chemical gradients that life exploits. If water was abundant, the chemistry follows. Solutes, mineral deposits, thermal gradients. These create microenvironments where replicating chemistry could conceivably organize into metabolism. The numerical detail matters: salinity ranges, pH values, and the presence of iron and sulfur species all alter the plausibility of life-friendly niches. Yet the record that remains is patchy. Rocks preserve mineral histories, but they are subject to alteration by later heat, radiation, and impacts. The numerical uncertainty is itself a character in this drama, a stubborn arithmetic absence. 3. Atmosphere and pressure. A planet needs a blanketing atmosphere to hold liquid water on its surface. Mars today presents an atmosphere less than 1% of Earth's pressure, far too thin to sustain stable lakes at the surface for long. But early Mars likely had a much thicker envelope. Estimates vary, and the models are thorny. Volcanic outgassing could have supplied copious carbon dioxide and water vapor. Impacts could have stripped some of it. Solar wind, unimpeded by a magnetic shield, could have gradually eroded what remained. Numerical reconstructions suggest pressures possibly comparable to Earth's in the most optimistic scenarios, but more conservative models place the early atmosphere at fractions of an atmosphere, enough, perhaps, to sustain transient but substantial bodies of liquid water. These numbers, the number of bars, the amount of greenhouse warming required to keep water liquid under a fainter young sun, form a narrow corridor of feasibility. If the early atmosphere stayed above a certain threshold for long enough, weather could become persistent, erosion could sculpt landscapes, and biochemical cycles could stabilize. If it collapsed quickly, then oceans could freeze and sublime, leaving salts and minerals instead of life-bearing chemistry. The arithmetic of atmospheric retention is therefore crucial to any careful speculation. 4. Energy inputs. Life requires energy. On Earth, energy comes from the sun, from chemical gradients produced at hydrothermal vents, and from the internal heat of the planet. Mars sits further from the sun. It receives roughly 43% of the solar flux the Earth does. Numerically, that is significant. A dimmer sun at a greater distance makes the climate problem harder to solve. Yet Mars may have had internal heat sufficient to drive hydrothermal systems for prolonged periods. A combination of solar-driven surface ecosystems and chemically rich subsurface habitats could have coexisted. Here, numbers converge with expectation. How much solar energy strikes a square meter of Martian surface? How much thermal flux can be produced by crustal radioactivity and residual formation heat? How frequently do geysers or hot springs punch through to? Provide local high-energy environments. The distribution of energy matters as much as its magnitude. A planet with limited surface habitability could still host thriving subsurface biospheres fueled by chemical energy escaping through rock fractures. Those would look very different from the sunlit coastal ecologies that dominated Earth's narratives. The numerical possibilities open, alternative evolutionary pathways, ones that could compress timescales or favor different organizational strategies. But they also complicate detection. Subsurface life leaves subtler signatures and is harder to preserve on the surface. 5. Geological activity and preservation. On Earth, plate tectonics recycles crust, buries and metamorphoses sediments, and both conceals and reveals fossils. Mars, by contrast, appears to have a stagnant lid for much of its history. That has two consequences. One, its ancient surfaces can remain exposed for billions of years, preserving a record that on Earth would have been erased. 2, without the constant churning of tectonics and a biosphere's tectonic feedback, some kinds of life-driven signatures might never become globally pervasive. Numerically, crater counting gives ages. Large expanses on Mars appear to be 3, 5 to 4 billion years old. Those surfaces have endured. In terms of preservation, the cold and dry state that followed Mars's active period is both a curse and a blessing. Low erosion rates and minimal biological turnover mean that a fragile anomaly, an unusual mineral deposit, a structured lattice of rock that hints at purposeful arrangement, could persist for eons. Conversely, the same dryness that preserves can also promote chemical weathering that obliterates organics, and cosmic radiation can degrade molecular traces over timescales of millions to tens of millions of years if they sit exposed. 6. Catastrophic impacts and violent resets. The early solar system was violent. The late heavy bombardment, if it occurred in the traditional sense, pumped the inner system with asteroidal and cometary missiles. Each impact is a numerical event, a probability distribution of sizes, frequencies, and energies. On Mars, a single basin-forming impact can sterilize vast regions, strip atmospheres, and reset local chemistry. The cumulative number of such events in Mars's early history is high. That creates a rhythm, windows of relative calm during which life could arise, punctuated by cataclysms that could prune evolutionary trees or erase physical artifacts. In thinking about an ancient intelligence, if such a thing ever had any plausibility, one must grapple with these numbers. How long between sterilizing impacts in any given region? How deep would shelter need to be to survive repeated bombardments? How would one's technologies built of materials susceptible to corrosion, abrasion, and radiation, withstand the trauma of billions of years, the arithmetic of impacts is a sobering counterweight to romantic speculation. 7. Timescales for intelligence and technology. If one frames the question as the emergence of technological beings, the sort that build durable monuments, manipulate metals, or alter their environment in ways that leave clear, persistent traces, then the relevant numbers are the evolutionary tempos. On Earth, microbial life appears early. Multicellular life arises much later. Technological civilization, the complex, energy-intensive stage capable of leaving archaeological signatures visible from orbit, emerges only in the last few thousand years. From the first hints of life to the present day span some 5 to 4 billion years on Earth. That is a pattern, not a law. If Mars's habitable window was brief by Earth standards, then the probability of reaching technological complexity by the same pathways may be low. But the numerical argument can be reframed. If life can adapt to different constraints, if selective pressures on a smaller, colder world favor rapid sociality or biomolecular innovations, then the time required might shrink. The problem with this line of thought is that it multiplies unknowns. It substitutes plausible alternatives for data. Still, numbers anchor the conversation. They demand that speculation acknowledge how steep the climb from simple chemistry to civilization usually is, at least by the single example humanity has direct access to. 8. Detectability and the silence of the record. Even if a niche or a network of niches on Mars once hosted complex life, the odds that their handiwork would be obvious today depend on preservation and detectability metrics. Durable artifacts, large monolithic structures, are improbable in many worlds, and their survival over billions of years requires protection from impacts and erosion. Chemical biosignatures, molecular fossils, and isotopic anomalies decay or are altered. Radiation penetrates only so many meters. Shielded environments can harbor the record, but make it hard to access. The numerical calculus here is unforgiving. Many decay processes operate on geological timescales that outpace the survival of fragile evidence. This is why the red planet's silence is not an argument for absence so much as a statement of expectation. Given the temporal scales and destructive processes, the most likely preserved signatures are those that are robust, abundant, and deeply buried. Sparse, ephemeral signals, however meaningful to contemporaneous observers, are likely overwritten. What the numbers ultimately do is temper desire with context. They do not eliminate wonder, they organize it. They tell a story in which possibility remains, but is bracketed by constraints, narrow windows of habitability, energy budgets that limit ecosystem size and complexity, bombardment rates that prune evolutionary branches, and preservation dynamics that erode the archaeological record. And yet there is an emotional economy to these figures as well. Mathematics and measurement can feel cold lists of bars of pressure, fluxes in watts per square meter, ages in billions of years, but placed against human time they become almost unbearably intimate. A billion years is more than the sum of its numbers. It is a backdrop against which human history is a brief smudge. To imagine a mind that arose and vanished across such spans is to confront the smallness of anyone's civilization's trace. The numbers are not only constraints, they are poetic reminders. This is why the opening question matters. It refuses to be purely rhetorical. It asks for humility in the face of deep time and for a rational reckoning with what is measurable. It invites a discipline of imagination to hold two thoughts at once. On the one hand, the wonder at what might have been. On the other, the rigorous accounting of what could endure and what must have been lost. In that tension lies the narrative power of Mars as a thought experiment about erasure, resilience, and the thinness of evidence. Ultimately, the red planet stands as a mirror, reflecting humanity's own anxieties about permanence. The numerics teach that Earth's record is itself precarious, that mountain ranges rise and fall, seas flood and drain, atmospheres are gained and lost. If one accepts that the preservation of a civilization's artifacts is a fragile affair, then one must also accept that absence of evidence is not always evidence of absence. The numbers put a probability distribution around that acceptance. They do not grant certainty, they insist on method. The question remains, if Mars once had all the conditions that, in principle, make life and even intelligence possible, why does the record not shout back? The numerical answer is a catalogue of diminishing odds and fragile survivals, the human. Answer is that absence, silence, and erosion are themselves meaningful. Together, they see the quiet urgency to explore, to seek the buried and the overlooked, to look not only for sculptures and ruins, but for isotopic fingerprints and mineralogical oddities, things that the arithmetic suggests are the most likely survivors of a lost wet epoch. In the interplay between speculative dreaming and careful counting, the narrative takes shape. Mars is not a blank canvas, but a ledger of possibilities, each line written in units of time, pressure, and energy, and each line asking that observers, humanity, future observers, read with both imagination and restraint. Imagine a ledger written in stone, each thin layer a sentence, each mineral grain a word. When geologists read the Martian stratigraphy, they do not read myth. They read a record of processes, sediment laid down by flowing water, salts left behind as lakes evaporated, clays formed where rocks met neutral pH fluids. Those pages, worn and incomplete, nevertheless tell a sustained story, not merely that water once flowed on Mars, but that it did so in ways that could have produced stable, habitable environments for geologically long spans of time. The question that follows is precise and almost painfully human. If the planet carried such a record of warmth and liquid, what traces, chemical, morphological, structural, might survive the slow erasure of deep time? The first, the most visible class of evidence is geomorphology. From orbit, Mars displays networks of branching valleys, winding channels, and fan-shaped deposits that read unmistakably as the handiwork of running water. The valley networks, particularly dense in the ancient highlands, possessed dendritic patterns analogous to terrestrial river systems shaped by precipitation and overland flow. Their occurrence is not random. They cluster in Noachian-aged terrains, the oldest visible surfaces dated by crater counting to roughly 3.841 billion years ago. Those networks are not the result of a single flood. They imply integrated drainage systems, repeated storms, and the slow incision of landscapes over time. In places where channels empty into basins, orbital cameras reveal deltaic lobes, layered sediments fanning outward like the fluted skirt of an ancient river mouth. Those deltas are not mere textures. They are archives of deposition, of sediments sorted by flow regimes, sometimes stacked in dozens of meters of stratigraphy. To assemble a delta of that scale requires persistent bodies of standing water and sustained sediment supply, conditions that, in terrestrial analogues, often persist for thousands to millions of years. Then there are the outflow channels, giant scars telling of far more explosive hydrological episodes. These features, such as the circumcrist channels, appear to have been carved by cataclysmic floods, torrents released when subsurface aquifers breached or when ice-laden reservoirs catastrophically melted. The coexistence of valley networks and outflow channels paints a complex hydrologic portrait, a planet that experienced both serene, slowly accumulating lakes and sudden, violent flushes. Each mode creates different preservation potentials for life. Slow deposition in fine sediment favors entombing and preserving delicate organics. Violent floods tend to abrade and disperse. The stratigraphic record thus contains both the promise of preservation and the threat of obliteration. Mineralogy supplies the next set of clues. Remote spectrometers and lander-based instruments have mapped the mineralogical fingerprints of water. Phyllosilicates, clay minerals formed by prolonged interaction with liquid water at neutral to mildly alkaline pH, dominate much of the ancient terrains. Their presence signals conditions that on Earth are friendly to complex prebiotic chemistry and biological activity. In contrast, younger Hesperian terrains show abundant sulfates and other evaporites, minerals often associated with more acidic, oxidizing waters. That stratigraphic shift suggests a transition, an early Mars with neutral, temperate, aqueous environments giving way to a colder, more acidic planet. This transition is crucial because it frames a temporal window during which conditions were not only wet but chemically accommodating to life's building blocks. These mineral signals are not merely theoretical. They are tactile, measured phenomena. Opportunity's exploration of Meridiani Planum revealed outcrops rich in sulfates and, strikingly, small hematite spherules, nicknamed blueberries, which formed as concretions in wet sediments. The Spirit rover and the Gusev plains detected high silica deposits around the home plate formation, silica that, on Earth, can be associated with hydrothermal alteration. Curiosity, within the layered walls of Gale Crater, has uncovered mudstones that were once lake bed sediments, replete with clay minerals and organics preserved within fine-grained matrices. Perseverance, now sampling the Jezero crater delta, drills into ancient river-made strata that likely settled in a long-lived lake. Each of these discoveries is a small proof water did more than wash rock. It altered chemistry, concentrated minerals, and laid down beds capable of trapping and sheltering organic matter. Chemistry complicates and enriches the story. The search for organic molecules on Mars is a tale of tantalizing finds and methodological caution. In 1996, the meteorite ALH-8401, ejected from Mars and recovered in Antarctica, carried within its carbonate globules polycyclic aromatic hydrocarbons and structures that some interpreted as possible microfossils. A claim provoked heated debate and, ultimately, a more conservative consensus. The features could be produced by abiotic processes, and terrestrial contamination could not be fully excluded. The lesson was not scientific failure, but humility. The Martian record is ambiguous, and human eagerness can outrun the evidence. Since then, in situ analyses have provided more robust, if still circumspect, chemical evidence. Curiosity's SAM instrument detected chlorinated organics in 2004 and later reported a richer suite of organics in ancient mudstones, molecules that survived more than 3 billion years because they were bound within the protective embrace of clays and salts. Those molecules are not proof of life. They are merely evidence that organic chemistry can be preserved on Mars under the right conditions. Perchlorates, discovered by the Phoenix lander in 2008, add another layer to this problem. These highly oxidizing salts can destroy organics when heated, complicating the interpretation of pyrolysis-based analyses. They are a reminder that the detection of ancient organics is as much about taphonomy, the processes of decay and preservation, as it is about origin. Methane provides another enigmatic thread. On Earth, methane is produced by both biological and geological processes, and its presence can be episodic. Instruments on Mars have detected transient methane spikes in the atmosphere, measurements that appear inconsistent across platforms. Rover-based instruments have recorded seasonal variations and brief plumes. Orbiters designed to map trace gases have sometimes failed to reproduce those detections. The discrepancy could arise from localized, sporadic releases, perhaps from subsurface reservoirs, clathrate destabilization, serpentinization reactions, or even contemporary biological processes. The inconsistency intensifies the mystery. Something in the Martian subsurface may still be active, but whatever it is, it hides well. Morphological signatures of life, the sort that drove early discoveries on Earth, stromatolites, microbial mats, microfossil filaments pose even more daunting interpretive challenges on Mars. Layered carbonates, laminated sediments, and certain microstructures can be produced by abiotic sedimentary processes, diagenesis, or by mineral nucleation in evaporitic settings. The scale matters. Microscopic structures require laboratory-grade resolution, chemical context, and an understanding of diagenetic overprinting to exclude non-biological origins. This is why the current strategy is both conservative and methodical. Seek congruence across independent lines of evidence. A morphological anomaly accompanied by isotopic fractionation and organic molecular complexity would be compelling. A single hint, however beautiful, remains equivocal. Preservation, taphonomy, anchors the entire enterprise. Deep time is a relentless eroder. Cosmic radiation and oxidative soils degrade organics at exposed surfaces over millions of years. Solar ultraviolet radiation, unfiltered by a thin atmosphere, bleaches and breaks down molecules. Yet burial can be protective. Fine-grained sediments, rapid sedimentation within deltas or lakes, and mineral matrices such as clays and sulfates can shield organics from radiation and chemical destruction. The very processes that form deltas and mudstones, rapid deposition, low oxygen conditions, and mineral encapsulation are precisely those that favor long-term preservation. Thus, the best places to look are not the grandest landscapes, but the quietest, buried beds, the innermost laminae of a delta, concretions grown in groundwater, veins deposited by hydrothermal fluids. Mars preserves those contexts in abundance. The planet's ancient surfaces are, in some senses, better archives than Earth's. Without pervasive plate tectonics and with limited erosional turnover after the planet dried, much of the Noachian record remains at or near the surface. That is both an opportunity and a paradox. Opportunity, because archives that on Earth were recycled into the mantle can be read on Mars. Paradox, because exposure also invites radiation-driven degradation. The geologic paradox is embodied in the Martian crust, ancient, largely preserved, and yet damaged by a host of post-depositional processes. One must also reckon with the planet's magnetic past. Measurements of crustal magnetization by Mars, global surveyor revealed remnant magnetism locked in ancient rocks, evidence that Mars once harbored a global magnetic field. A magnetic dynamo of the past would have shielded the atmosphere and surface from the worst of solar wind erosion, promoting atmospheric retention and, with it, climatic stability. The loss of that dynamo is part of the environmental story. It marks a point after which atmospheric stripping accelerates and surface habitability becomes more precarious. The timing of that loss intersects with the mineralogical and geomorphic transitions, a warmer, wetter Noachian, perhaps shielded by magnetism, giving way to a colder, drier, later Mars. All of these threads, geomorphology, mineralogy, chemistry, preservation dynamics, and magnetism, compose a chorus rather than a single voice. Each instrument of exploration records a note that may be harmonized into a plausible narrative. Ancient Mars contained environments that, by terrestrial standards, were habitable for sustained intervals. The delta deposits at Jezero, the clay-rich mudstones of Gale, the concretions and silica anomalies at Meridiani and Gusev, together they sketch a planet that offered lakes, hydrothermal systems, and groundwater places where metabolism might have been energetically feasible and where sediments could entomb biosignatures. Yet the ledger is partial, and the handwriting can be coy. Meteorite records are fragmentary, orbital spectral signatures are sometimes ambiguous, and in situ chemistry can be confounded by modern oxidants. Scientific humility demands that each positive signal be weighed against alternate, abiotic explanations. This conservatism is not an intellectual dourness, but a methodological necessity. It is the form that careful wonder must take when confronted with the immense timescales and the many filters that time imposes on evidence. There is, finally, an emotional cadence to this evidence. The stones do not shout. They whisper in layered sediments and mineral textures, in faint organics and in transient gases. That whisper is enough to keep the scientific community probing, drilling, caching samples for eventual return to Earth, pushing instruments to millimeter-scale resolution, and mapping trace gases with unprecedented sensitivity. Each new layer of data tightens the constraints and refines the questions. The absence of decisive, loudly obvious fossils is not failure. It is a reminder of the fragility of traces and of the patient labor required to read them. If ancient Mars hosted environments stable for hundreds of millions of years, then the planet offered opportunities for life to begin, diversify, and perhaps explore complexity. The existing evidence, valley networks, deltas, clays, concretions, preserved organics, transient methane, does not prove that life rose to intelligence, nor does it close off the possibility. Instead, it reframes the question, not whether Mars was habitable in the abstract, but how those habitable regions were distributed, how long favorable chemistries persisted in any given place, and how deep, how quickly, and under what mineralogic regimes potential biosignatures could be preserved. The record is intricate and incomplete. It demands a multifaceted detective work that is at once exacting and imaginative. In that way, the traces that Mars preserves do more than supply data. They alter the scale of wonder. They replace a single sensational claim with a series of careful inferences, each with its own probability and its own margin of uncertainty. To read Mars's ledger well is to accept a different kind of thrill, the slow accrual of plausibility rather than the sudden discovery of certainty. The sedimentary pages turn slowly, and within them lie the most poignant of possibilities, that a world once warm and wet offered niches where life's chemistry could play out, that some products of those processes were sheltered and preserved, and that perhaps somewhere in those preserved pages a faint, interpretable record awaits those instruments patient enough to uncover it. What does it mean when stone arranges itself into something that looks intentionally made? What should a mind do when geometry on a planetary face begins to read like a signature? The question is small and particular, but it carries a psychological weight disproportionate to its size. Faces, straight lines, and sharp angles have a way of acting as cognitive tripwires. They trigger pattern recognition machinery honed for social life, and across cultures they have summoned stories about agency and makers. On Mars, those triggers have been set loose on a landscape that is itself a palimpsest of processes measured in billions of years. The result has been one of the most persistent and evocative ambiguities in the modern history of planetary science. Geological unnaturalness that insists on interpretation. The most famous case is plain and simple in its mythology, a humanoid visage seen in low-resolution orbital photographs. In 1976, the Viking orbiters returned images of a mesa region in the northern hemisphere, Cydonia, that, under a particular lighting geometry and at a coarse resolution bore a striking semblance to a face. The image was not only data, it was a catalyst for imagination. Newspapers printed the photograph as if it were an emblem. Commentators and the general public, encountering the unmistakable suggestion of eyes, nose, and mouth carved into an alien plane, found themselves tempted toward a narrative that was both ancient and humane, the discovery of a relic, the remnant of a mind. That temptation is instructive. It illuminates not only the psychology of perception, but the cultural hunger for continuity and meaning in a universe that otherwise measures human presence in a handful of breaths against the geological record. Yet the scientific response to the face followed a different tack: reobserve, increase resolution, change viewing angles, and model the topography. In the late 1990s and early 2000s, higher resolution imaging from later orbiters resolved the face into a natural mesa, complete with cliffs, terraces, and shadow patterns consistent with differential erosion. When instruments capable of sub-meter resolution later painted the topography in even finer strokes, the facial features dissolved into the expected variability of rock, light, and shadow. That bare account risks being too tidy. The public and a portion of professional commentators continued to linger on what the face represented, an emblem of possible ancient intelligence wiped almost entirely by time. The tug between human longing and methodological caution, between a seductive image and the imperative to falsify, has been instructive because it exposed the mechanics of how humans read the record of deep time. The face is less a scientific question with a single answer than it is a test case for the disciplines of interpretation. What counts as evidence when the record has been abraded by billions of years? Beyond the face, satellites have revealed other anomalies: long, straight lines marching across plains, sharp pyramidal silhouettes, oddly regular polygonal patterns, and clusters of angular mounds that seem to betray design. Each of these discoveries provokes similar reactions: a spike of speculation, a flurry of media interest, and then the slower, more patient work of analysis that seeks natural explanations. The geological vocabulary that can produce apparent artificiality is longer than popular imagination often allows. Wind-carved yardangs can throw up crisp ridgelines, joint-controlled erosion fractures, bedrock into rectilinear mesas, lava flows. Meeting heterogeneous substrates form angular outlines. Dikes, sheets of solidified magma resist erosion and present as straight ridges. Periglacial contraction in frozen soils produces regular polygons. Salt weathering can sculpt honeycomb patterns. On the right scale and under the right light, these natural forms can mimic geometry that, at a glance, seems deliberate. One must remember how images are made. The resolution of the early Viking frames, measured in the hundreds of meters per pixel, conflated subtle topography with sharp shadow contrast. At a coarse scale, a mesa's shadowed terraces can fuse into an apparent eye socket. A row of boulders at a particular angle can read as a mouth. Higher resolution data changes the narrative, not by disproving the original observation's reality, but by revealing the complexity that coarse optics had compressed. Modern cameras, with sub-meter resolving power and the ability to construct digital elevation models, let investigators decompose a face back into slopes, terraces, and joints. Three-dimensional reconstructions remove much of the ambiguity caused by sun angle. Yet that still does not exhaust the phenomenon, it simply reframes it. There is also a deeper reason why geometric regularity crops up in geology. Nature, left to its own devices over long timescales, is not always random. Stress fields in rock, governed by the physics of fracture, produce orthogonal joint sets with striking regularity. Cooling contraction in basalt lava yields columnar joints, columns with hexagonal cross-sections that can appear almost manufactured in their precision. Salt diapirs in evaporite tectonics can produce domes and polygons. Layered sedimentary beds interspersed with harder and softer strata erode into stepped forms. Under arid conditions, those steps take on sharp edges. When fluids percolate along fractures, they may precipitate minerals in linear veins that later resist erosional forces, leaving straight ridges where landscape once was. Across scales, the microscopic lattice of a crystal, the meter-scale hexagons of basalt, the many-kilometer linearity of dike swarms order emerges from the laws of physics without any agency at all. The persistence of public fascination with alleged ruins therefore has less to do with the likelihood of artificiality than with the human habit of seeking narrative continuity in the face of erasure. The emotional economy of a face on Mars is rich. It offers consolation to smallness, a way to imagine a sentient continuity across the yawning gulf of time. Such an image promises an answer to the uneasy question raised by the deep time arithmetic, the possibility that the cosmos does not only create and destroy, but also remembers. That promise is powerful, but it is also precisely why science responds with a toolkit designed to resist seductive conclusions, repeat observation, controlled hypotheses, comparative analogs on Earth, and quantitative analysis. Quantitative approaches to the problem have matured. Analysts use edge detection algorithms, symmetry metrics, and statistical tests to assess whether a given form deviates from natural morphologies. Fractal dimension, angular distribution statistics, and Fourier analysis help separate noise from structure. If an object displays bilateral symmetry beyond what would be expected from random erosion, or if its features align to rational geometric proportions with high statistical significance, then its artificiality becomes a hypothesis worth elevating. But the results, time and again, have favored natural processes. Many of the straight-line features correlate with known fracture or dike patterns apparent pyramidal forms map onto. Stratigraphic layering, where resistant caprock protects an underlying edifice and erosion, carves amphitheaters into regular steps. The methods are not metaphysical, they are practical. They take the gestalt impression, the face that reads like intention, and interrogate it with measurements that must withstand scrutiny. Yet not all anomalies are presently explained. There remain instances of straightness, orthogonality, or regularity that do not yet map neatly onto a clear physical process. In those cases, science holds a posture of provisional ignorance, a recognition that complexity and the patchiness of observations can leave gaps. This posture is different from the romantic leap to agency. It requires cataloging, more and better data, and the patient construction of models that might find a place for the oddity within the known physics of planetary surfaces. Sometimes, further observation reveals a mundane origin. Sometimes, a plurality of processes is required, and occasionally, the modeling encounters genuine unknowns that stimulate new lines of inquiry into Mars's geologic history. The tension between imagination and method is also a mirror for the human relationship to evidence more broadly. The face and its kin act as pedagogical moments. They show how perception, culture, and expectation condition the reading of ambiguous data. They also reveal something about temporal scale. A sculpture or wall built and then subjected to billions of years of impact gardening, thermal stress, and chemical weathering would look very different from the crisp ruins immortalized in fiction. Time is a sculptor as relentless as it is amoral. It tends to smooth, to blunt, and to scatter even surprisingly robust materials. Dense, igneous rocks fragment into rubble fields and talus. Metals corrode, concrete spaw, and the signatures of manufacture diffuse through repeated cycles of deposition and erosion. The arithmetic of deep time makes the survival of clear, intentional structures into the present an unlikely scenario unless they were buried and protected shortly after construction, the very circumstance that would make them invisible to orbital reconnaissance. That consideration reframes the search for artificiality in practical terms. If a civilization once existed on Mars and left behind artifacts, their best chance of surviving deep time is to have been deeply buried in a protective matrix encased in fine sediment, sealed within permafrost, or caught in mineral concretions. Unburied monuments, standing in the open, are poor candidates for survival measured against a planetary clock. This is the lesson that geology brings to the table. Preservation favors quick burial and chemical stability. That lesson is one reason why the most scientifically defensible searches for past life or past intelligence focus less on striking visual anomalies at the surface and more on subsurface stratigraphy, sedimentary contexts, and chemical basins where the taphonomic conditions for preservation were favorable. There is also a cultural lesson. The face galvanized a public appetite for sense-making, for cosmological continuity, and for narratives that made the immensity of time comprehensible. It also provoked a countervailing scientific rigor, a demand for replicability, for cross-instrument confirmation, and for an appreciation of scale. Both responses are human and necessary. Wonder drives exploration. Rigor makes its findings reliable. The interplay between those forces is, perhaps, the essential engine of scientific culture. Mars, by offering images that read like artifacts and then revealing the physical explanations, teaches humility. It teaches that the imagination can be a prism that amplifies some readings of data while the method offers the corrective lens. Ultimately, the geometry that looks unnatural on Mars says something fundamental about the world's ability to produce patterns that resonate with human cognition. It also says something about the limits of reading deep time at a glance. In the architectural economy of geology, straightness and symmetry are not exclusive proofs of intention. They are often the signatures of long-running physical processes. The face, the lines, the pyramidal mesas, they will continue to be points of attention, not because they are closed cases, but because they are fruitful ones. They are invitations to improve instruments, to model processes with greater fidelity, to revisit old images with new mathematics, and to think more carefully about what preservation over eons actually entails. For those who study Mars, the lesson is not antiseptic. There is a lingering affective dimension, the quiet gravity of facing an image that seems to answer humanity's oldest questions about company and continuity. That gravity is part of the work. It motivates better surveys, more sensitive spectrometers, and the insistence on subsurface exploration that can read the planet's ledger with finer detail. It is why missions now prioritize stratigraphic context, why sampling campaigns seek the most protective sediments, and why high-resolution altimetry and multispectral mapping are central to current orbital programs. In the grand ledger of deed time, the face is a small but memorable line. Whether it is a suggestive mesa or a misread monument of nature, the episode mattered because it taught how to balance hunger with discipline, desire with measurement. The geometric anomalies that remain, those straight lines that refuse tidy explanation, the polygons that suggest stress fields unaccounted for, the sharply edged mounds, are the places where the planet still whispers. They are not yet proof of makers, nor are they evidence that no makers could ever have existed. They are, in the end, prompts, calls to look more carefully, to model more faithfully, and to acknowledge the vastness of time that both preserves and erases. In that tension lies the continuing drama of Martian exploration, a patient decoding of patterns that may be purely natural, or that may one day contain a different kind of message, subtle and deeply buried, waiting for instruments wise enough and patient enough to read it. What happens when a single shadow, caught at a single moment by a single camera, can reorder an entire conversation about the nature of life and memory in the solar system? That is the modest and explosive question that begins the Cydonia episode, a mesa on a distant plain, photographed in 1976 by instruments orbiting Mars. Presented at coarse resolution and under a slant of light that made a block of stone look uncannily like a face, the image landed in newspapers and in imaginations with the speed of rumor. For a moment, the possibility that planet-scale history might include the traces of a vanished intelligence felt suddenly, insistently plausible. The image was a small thing, pixels arranged, shadows pooling, human pattern recognition wired to see eyes and intent, but its cultural force was immense. It asked, implicitly and without ceremony, whether time itself might keep secrets. From that point, the hypothesis space bifurcated. One path led to gentle skepticism that human perception, trained to read faces and agency, had simply been tricked by geometry, light, and low resolution. The other path, more dramatic and more costly in imagination, asked what kinds of makers, materials, and preservation regimes could produce durable artifacts that might survive millions or billions of years on a planet like Mars. Between those paths, there is not a mere contest of credulity, there is a map of testable ideas, each with practical consequences for how the search for past life and past intelligence should proceed. The first, and often most useful hypothesis, is the psychology of perception, pareidolia. The human brain is an associative engine, highly optimized for pattern detection. Faces are not neutral stimuli, they are social magnets. When orbital cameras returned, low-resolution mosaics, images sampled at scales of tens to hundreds of meters per pixel, subtle. Variations in slope and albedo became fused into emblematic patterns. Under variable sun angles, terraces, and escarpments projected shadows that, to a mind primed for meaning, aligned into nostrils and brows. Pareidolia is not an error in the laboratory sense, it is an evolved tool that dramatically lowers the threshold for false positives. In the interest of rapid social judgment, from a scientific point of view, the test for pareidolia is straightforward. Reobserve at higher resolution, change illumination geometry, and construct three-dimensional topographic models. Those steps, taken in the decades after Viking, repeatedly resolved the face into a coherent natural mesa slopes, fractures, cap rock, and removed much of the initial mystery. The lesson here is methodological. Extraordinary impressions require repeatable, multi-angle verification. A second hypothesis is geological mimicry. The planet's physical laws routinely produce order that can read as artificial to a casual observer. Thermal contraction, jointing, differential erosion, layered stratigraphy capped by resistant lithologies. These processes, governed by mechanics and chemistry, yield straight edges, orthogonal fractures, polygonal patterns, and even near-symmetric features. On Earth, hexagonal basalt columns, dike swarms cutting across plains, and periglacial polygons demonstrate that geometry need not imply design. On Mars, where ancient crustal stresses, vast lava flows, and the freeze-thaw dynamics of permafrost have had eons to play out, such patterns are abundant. The testable predictions of the geological hypothesis include correlations with known structural trends, faults, dike orientations, mineralogical signatures consistent with erosion, resistant caprocks, and the presence of step-like terraces where strata of varying hardness weather at different rates. High-resolution imaging, digital elevation models, and mapping of subsurface structures via radar typically confirm these expectations. Yet the existence of natural mimics does not settle the matter for everyone. That is where alternative hypotheses emerge, scenarios that imagine agency but place it in different temporal and material contexts. One speculative class posits deliberate construction, that some form of intelligence once shaped stone on Mars in ways we might now misread or only partially perceive. If that were so, what would the makers have produced, and under what constraints would those works survive? The arithmetic of deep time quickly complicates any straightforward romanticism. A structure left exposed to billions of years of impacts, thermocycling, cosmic radiation, and chemical weathering stands a poor chance of keeping crisp lines. Even robust igneous rock will fracture and degrade, exposed metals will corrode and crumble, concrete-like composites will spall. The preservation equation favors burial and mineralization, rapid sedimentation into a delta, encapsulation within volcanic ash, permafrost entombment, or concretion formation within groundwater are the kinds of taphonomic pathways that can preserve morphology and chemistry across geological epochs. Thus, if an intelligence once created artifacts on Mars, their best chance of surviving into the present would have been to be quickly buried and sealed in a protective, low-oxygen mineral matrix. From this insight flow concrete predictions and tests. An artificially shaped object, if it were buried, might still betray itself via anomalies in local stratigraphy. Abrupt changes in sedimentary grain size, trace element concentrations inconsistent with regional geology, or electromagnetic signatures that stand out against background. Seismic reflection studies could, in principle, reveal coherent density contrasts at depth. Ground-penetrating radar can map subsurface layering and detect buried rubble or hollows. Geochemical assays of drilled cores might reveal unexpected alloys, polymers, or isotopic anomalies that are difficult to generate abiotically. Each of these paths is instrumentally demanding, but they are not metaphysical. They convert speculation into a program of observation. A different set of possibilities takes materials science seriously and asks what kinds of materials could last. Metals oxidize, ceramics crack, organics decay. But stone sculpted into complex form or geological features selectively enhanced by directed weathering could survive for long durations if quickly protected. The most conservative, and therefore most plausible, material hypothesis is that any surviving artifacts would be expressed not as freestanding monuments, but as anomalies in geological context, unnatural geometry preserved inside concretions, odd compositional layers, or high-precision milling marks at microscales, features that survive because they are embedded and protected, not because they stand tall on the open plain. Another speculative route imagines biological agency rather than direct lithic sculpture. On Earth, organisms can engineer landscapes at scales large and durable. Stromatolites, reef structures, and bryozoan and coral builds are biological architectures whose fossilized remnants persist. Could some form of life on Mars have shaped sedimentary forms at scale, biofilms precipitating minerals into regular patterns, microbial mats molding sediment into laminae with semi-regular textures? If so, the signature would be chemical as much as morphological isotopic fractionations, specific organic biomarkers preserved within mineral matrices, or biomineral fabrics inconsistent with abiotic precipitation. The test here relies on multidisciplinary convergence. Morphological regularity accompanied by molecular complexity and isotopic anomalies strengthens the case for biogenic origin. There is also the exogenic hypothesis that external processes, meteorites, volcanism, or impact ejecta could deposit materials that imitate structured forms. A large impact can fling blocks over vast distances, sorting them into unusual arrays. Volcanic intrusions can form linear ridges. Landslides can pile debris into apparent terraces. The predictive signature of these processes tends to be chaotic at finer scales. lacking the repeated modularity or purposeful symmetry one might expect from constructed works. Where exogenic hypotheses have explanatory power, they often make specific, falsifiable claims about lithology and depositional features. For each of these hypotheses, the scientific imperative is the same: develop an evidence chain that demands consistency across multiple independent lines of inquiry. Morphology alone is unreliable. Geology repeatedly demonstrates that the mind's urge to narrate can outrun the data. Chemistry alone is suggestive, but not definitive. Organic molecules can be abiotic, and isotopic shifts can have multiple drivers. The convincing case, if such a case ever emerges, will be one where morphology, chemistry, stratigraphy, and contextual geology align in a pattern that resists plausible abiotic explanations. There is a practical hierarchy to testing these ideas. At the top are non-invasive orbital surveys, high-resolution imagery across multiple sun angles, multispectral and hyperspectral mapping to identify mineralogy, synthetic aperture radar to assess subsurface layering, and gravity mapping to detect density anomalies. The next tier is in situ reconnaissance, landers and rovers that can image at millimeter scales, perform microstructural analyses, and extract cores. The most definitive and most expensive are sample return missions. Bringing physical material to terrestrial laboratories allows instruments orders of magnitude more powerful than those that can be flown, enabling isotopic dating, high-resolution petrography, and the search for trace organics in controlled conditions. The cost and logistics of sample return are large, but the potential to cross-examine competing hypotheses under the microscope is unrivaled. Numbers anchor these decisions. Orbital resolutions measure in centimeters to tens of centimeters per pixel for contemporary high-resolution cameras. The Viking images were at scales of tens to hundreds of meters per pixel. Cosmic ray flux at the surface degrades organics over millions to tens of millions of years when exposed. A few meters of regolith, however, significantly attenuate penetrative radiation. Impact, gardening, and micrometeorite bombardment mix and churn the upper regolith on similar timescales, threatening the survival of surface-bound signatures but leaving deeper records relatively undisturbed. Those orders of magnitude matter. They shape where to drill, how deep to penetrate, and what preservation regimes are worth prioritizing. Beyond technical feasibility, the Cydonia episode surfaces an ethical and cultural dimension. The image of a face on Mars tapped a deep human hunger to be seen by a cosmos that now looks so indifferent. That hunger can be a force for exploration, motivating funding, public interest, and political will. It can also be a liability, encouraging premature announcements and the misinterpretation of weak signals. The scientific community, learning from Cydonia's media firestorm, adopted a posture of cautious transparency, acknowledged the allure, but insist on reproducibility and convergent evidence. That posture is not merely protective of reputations, it guards against the social costs of false certainty in a field where the stakes our place in cosmic history are existential. Finally, the hypothesis space must be set against the scale of deep time and the fragility of memory. Even the best-preserved artifact is subject to a planetary ledger that is vast and indifferent. Geological processes both create and destroy. Preservation is the exception, not the rule. The arithmetic of survival is unforgiving. If a civilization rose and fell on Mars in a window hundreds of millions of years long, its traces would most plausibly survive where they were buried, mineralized, and shielded. The visual allure of surface ruins is therefore historically unlikely. That does not equal impossibility. It does, however, focus the search on the subsurface, on sedimentary basins, and on mineral contexts capable of sealing and protecting a record. Cydonia matters for another reason. It is a pedagogical moment in how humans interrogate ambiguous evidence. It teaches that wonder and skepticism are not opposites but complementary faculties. Wonder expands the range of hypotheses. Skepticism refines them into testable claims. The search strategy that emerges from this dialectic is patient and plural. Map broadly, drill strategically, analyze carefully, and return samples for the ultimate adjudication. Above all, it requires humility about what is visible from a distance and what is preserved in the dark. In the end, the unresolved doubts about Cydonia are less about the mesa itself and more about what the mesa revealed about human cognition and method. The face was a mirror. The image reflected as much about the observers as it did about the observed. It crystallized a set of questions, technical, philosophical, and cultural, that continue to shape how humanity seeks company in deep time. The proper scientific response is neither dismissal nor credulity. It is a disciplined curiosity, a commitment to follow where evidence leads, to design instruments to probe the buried, and to accept that, in a universe measured in billions of years, the faintest anomaly may be a whisper that requires patience, rigor, and the slow accumulation of corroborating lines of inquiry to be heard. What would it mean to imagine a civilization that rose on Mars, not by accident of panspermia or the hand of another world, but by the relentless, unguided play of chemistry and evolution on an alien shore? The thought tugs at two human instincts at once. The hunger to believe that intelligence is not a terrestrial monopoly, and a scientific reluctance to let longing outrun evidence. This section opens from that tension, asking a precise question that is at once numerical and existential. If life took hold on early Mars during its warmer, wetter epoch, could it, under Mars's peculiar constraint, have climbed from microbes into organized societies that left durable traces? The hypothesis is deceptively simple on its surface and fiendishly complex under the hood. It folds together a chain of contingent steps: the origin of replicating chemistry, the persistence of ecological networks, the emergence of multicellularity, the acceleration toward cognition and sociality, and then the leap to behaviors that alter environments at scales visible to later epochs. Each link in that chain depends on time, energy, material availability, and the interplay of chance and selection. To make any careful claim requires translating those contingencies into testable predictions and examining how deep time alters the odds. First, pathways from microbial life to complex societies. Earth's trajectory gives the only detailed template humanity possesses. On that world, life appears early in the record, but complex multicellular forms, and, later, cognitive complexity arise after long intervals punctuated by environmental upheaval and biochemical innovations. Oxygenation events, the evolution of eukaryotic cells, the advent of predation. Mars, if its habitable window was on the order of hundreds of millions to perhaps a billion years, might have had enough temporal room for some of these transitions, but the tempo need not mirror Earth's. Different selective regimes can compress or elongate evolutionary timescales. Consider the possible accelerants. On Mars, smaller planetary size and more extreme environmental gradients could concentrate selective pressures in unusual ways. Localized oases, long-lived hydrothermal systems, groundwater-fed lakes within crater basins, or coastal shelves of a putative northern ocean could have provided energy-rich, chemically diverse habitats. Within these islands of habitability, steep chemical gradients and mineral interfaces would have fostered metabolisms rich in redox chemistry. Where ecological complexity arises, so does the potential for the evolution of cooperation, division of labor, and rudimentary information storage, behaviors that, over many generations, can scaffold toward higher cognition. A second avenue opens through social evolution, not centered on primate-like intelligence, but on alternative architectures of complexity. On Earth, the most definitive ecological engineers, coral reefs, beaver dams, termite mounds, are not hominins. They alter environments profoundly and leave durable records. On Mars, a plausible analog is an organism or suite of organisms that engineered sedimentary or mineral matrices through biomineralization. Microbial mats can precipitate carbonates into layered stromatolites that fossilize. If Martian life favored mineral precipitating metabolisms, silica, iron, carbonate cementation, then entire sedimentary fabrics could bear the imprint of biology without any lithic monumentality. These are civilizations of place rather than tool users, distributed, collective, architectonic in the sense of sustained environmental modification, not of sculpted stone. This distinction matters because the signatures left by a social ecosystem of bioengineers will be chemical and textural more than structural in the macroscopic architectural sense. Concretions, ordered laminae, mineral fabrics with repeated modularity, and isotopic fractionations, especially significant deviations in carbon, sulfur, or iron isotope ratios compared to abiotic baselines, would be the fingerprints of such ecological civilization. The detective work, therefore, must be molecular and microstructural as much as morphological. If one presses the hypothesis toward technological intelligence, the sort that manipulates durable materials, different constraints come into sharp relief. Technology, as understood on Earth, depends on energy density, access to workable materials, an environment in which manufactured artifacts can be used and accumulated, and, crucially, a social transmission system for complex knowledge. Mars presents immediate challenges: lower solar flux, a thin atmosphere that reduces available surface energy, and thermal buffering, and the scarcity of accessible surface metals in oxidized soils. Fire as a technology is less straightforward in a low oxygen context. Smelting requires either local reducing atmospheres or deliberate chemical engineering. Those are not prohibitive conditions in principle, but they demand specific material pathways. On Mars, those pathways might have centered on stoneworking, ceramics, or the use of bioproduced minerals as pigments, adhesives, or binders, materials that, if buried early, could survive for geological times. Material survival is the next major link in the argument. Deep time is an unforgiving archivist. Exposed artifacts are vulnerable to impact gardening, thermal stress fracturing, acid salt weathering, and cosmic radiation. For anything to persist over billions of years, burial and mineral encapsulation are the primary preservational strategies. That changes the search. A buried stone wall or buried sequence of worked stones locked inside a deltaic deposit would stand a better chance of surviving than a standing monument on an open plain. Conversely, biological architectures, mineralized mats, biomineral precipitates can be preserved in finer-grained sediments as coherent fabrics, their microscale organization shielded from radiation and oxidative soils. From these considerations follow practical, testable predictions. If a Mars-origin civilization was biological and environmental in character, the record should show repeated mineral fabrics with morphological regularities inconsistent with abiotic precipitation, localized isotopic anomalies, indicating biologically mediated fractionation sustained across stratigraphic intervals, stacks of sedimentary laminae with microtextures and organic biomarkers arranged in patterns consistent with mat-building organisms. If the civilization developed technology, one should also expect anomalies in elemental abundances, trace concentrations of smelting byproducts, stable isotopic shifts produced by fractionating processes, inorganic compounds not readily generated abiotically in the local context, or microfabric march on lithic surfaces consistent with deliberate shaping. Importantly, a chain of corroborating signals, morphology, chemistry, stratigraphy would be far more convincing than any single line of evidence. Detection strategies follow directly. The places to look are not the brightest visual anomalies on the surface, but the most promising preservational contexts. Ancient deltas like Jezero, deep lacustrine mudstones, as in Gale, silica-rich hydrothermal deposits, and buried aquifer junctions. These contexts provide both the likelihood of habitability and a taphonomic refuge. Orbital hyperspectral mapping, ground-penetrating radar, and high-resolution altimetry can prioritize targets that show unusual compositional signatures or subsurface density anomalies. Rovers and ultimately sample return missions must target the innermost laminae of deltas and concretions, areas where microstructure and organic chemistry are most likely to be preserved. The protocol is not different in principle from the way paleontologists seek the most undisturbed bedding planes on Earth. The metrics, depth of burial, mineral matrix, exposure to oxidants, and the presence of protective clays are quantifiable. There is an arithmetic to preservation that shapes expectations. Radiation doses at the Martian surface degrade organics on scales of millions of years. A few meters of regolith materially reduce that flux. Perchlorates and oxidants scramble organics during pyrolysis. Based analyses, clement clays, and saline matrices can entomb them. The probability sketched by these numbers suggests that if any high-information technosignature exists, it is more likely to be found deep and chemically sequestered than superficially obvious. That conclusion reframes prior cultural obsessions with surface ruins and emphasizes the subsurface hunt. The hypothesis space also admits a radical alternative. Intelligence might have evolved along non-human lines, producing forms of social organization and environmental modification that do not map easily onto terrestrial analogs. A sentient organism could be aquatic, embedded in sediments, or even distributed across a colony-forming architecture whose artifacts are living biofilms. Its technology could be biochemical rather than lithic manipulation of metabolic pathways to structure sediments, engineered release of mineralizing compounds to create shelters, or the construction of semi-permanent microbial edifices. Detecting such a civilization would require an openness to non-lithic signatures, complex organics with polymeric structures not easily explained by abiotic synthesis, recurrent mineral assemblages tied to organic remnants, and spatial patterns in sediments that imply coordinated biological action rather than random deposition. The cautionary counterweight to these speculations is stark. Deep time narrows possibilities. Catastrophic impacts, atmospheric loss, and climatic decline prune evolutionary trajectories, and erase fragile records. The probability that a technologically manipulative species on Mars would both arise and leave easily interpretable, unburied monuments persisting for billions of years is low by the arithmetic of planetary processes. That does not render the hypothesis meaningless, merely unlikely in the sense of survival without burial. It transforms the search into a problem of where the best preserved archives might lie and how to read them with tools fine enough to detect microarchitectures of intelligence. Beyond the scientific logic, there is an emotional architecture to the hypothesis that cannot be ignored. To imagine a Martian civilization, whether a mat of mineralizing microbes or a networked society of tool users, is to step outside anthropocentrism and confront humility. The thought reframes humanity's sense of uniqueness, not by diminishing human value, but by situating intelligence as one possible outcome in a universe of long processes and rare junctures. The possibility that another mind once walked or grew on a neighboring world, then vanished without fanfare, presses a kind of poignancy, a reminder that durability is not the same as significance. Civilizations may be brilliant and local, then erased. If Mars indeed hosted such experiments in organized life, their loss becomes a lesson about contingency and fragility. This lesson has methodological consequences. It argues for a patient program of exploration that privileges careful stratigraphic sampling, interdisciplinary cross-checks, and an acceptance that conclusive answers will demand convergence across lines of evidence, technological capacity, better drills, contamination, resistant sample caches. The ability to map subsurface chemistry in situ becomes as important as speculative imagination. The narrative of possibility must be tethered to a program of observation designed to distinguish between elegant natural processes and genuine, if faint, signatures of organization. In the final analysis, the natural civilization hypothesis is not an assertion that Mars must have borne minds, it is an invitation to treat the question with both wild curiosity and meticulous restraint. It suggests a checklist of plausible pathways, preservation filters, and detection strategies, while acknowledging the crushing vastness of time. It reframes the search for company in the cosmos as a type of archaeology at planetary scale, one that must be sensitive to microtextures and isotopes as much as to grand facades. Whether the answer to the opening question is affirmative or negative, the exercise of asking it deepens the human relationship to deep time. It sharpens humility, amplifies wonder, and insists on sober, patient exploration of a ledger written in stone and mineral, a ledger whose most intimate lines may yet be buried beneath the rhythms of Mars itself. What if Mars was not merely a lonely experiment of chemistry, but a waypoint in someone else's itinerary? What if the red dust and sedimentary beds were not only the record of winds and water, but also the faint residue of intervention, an intersection, or an interference between natural history and purposeful contact? The idea is compact and unsettling, that Mars, for reasons both practical and strategic, might have been visited, seeded, or used as a staging ground by an intelligence not native to the planet. Framed as a thought experiment, the proposition forces a rearrangement of questions. It asks scientists to treat planetary geology not only as an archive of climate and chemistry, but as an overlapping palimpsest, where biological and technological signals could cross, mingle, and obscure one another. The scenario divides itself into a handful of vivid pathways. At one end sits unintentional transfer, the crude but real process of lithopanspermia. At the other sit intentional acts, directed panspermia, seeding experiments, or the placement of infrastructure for interplanetary travel. Each pathway carries its own physics, its own timescales, and its own signatures, and each collides with the same stubborn mediator, deep time. What might remain after billions of years of impacts, freeze-thaw cycles, and chemical weathering would be subtle, often ambiguous, and easily mistaken for a natural process. The problem therefore becomes one of interference, how to separate small, deliberate patterns from the cacophony of geologic noise. Lithopanspermia is the humbler mechanism. Rocks blasted from a planet by impact can cross space and seed another world. The solar system bears this logic as fact. Meteorites of Martian origin lie in Earth's deserts, their trapped gases a fingerprint of another planet's atmosphere. In that directionality alone there is a modest symmetry. Material moves between planets. Biology, if hardy enough, might hitch a ride. The numbers matter. Ejecta must attain escape velocity. survive the interplanetary radiation environment for potentially millions of years, and arrive at a target world at velocities allowing soft delivery rather than annihilating impact. Microbial spores, especially those shielded within rock pores, show surprising resilience in experiments. In vacuum and under radiation, survival probabilities fall but are not zero. Thus, the possibility remains that Mars and Earth could, in principle, exchange biological material. That exchange, however, does not require agency. It is a stochastic traffic of rocks and ice across a crowded early solar system. Directed seeding is a different animal. It imagines choice and intelligence deciding that Mars is a suitable substrate for life, or that Mars is an efficient node for distributing life to other worlds. Why Mars? Practical physics answers with blunt clarity. Mars sits close to the inner planets, has a lower escape velocity than Earth, and in its wetter epochs harbored accessible water and a thicker atmosphere. For a civilization capable of interplanetary travel, Mars would be easier to land on and to launch from than a larger world with deeper gravity wells. It offers stable basins, craters, deltas, and aquifers where seeding experiments could be run with relative control. A temperate northern ocean, if it existed, would present an ideal testing ground, a shallow shelf, variable chemistry, and contact with groundwater systems. From an engineering perspective, Mars is logically attractive as a laboratory, a depot, and a stepping stone. If seeding was intentional, what might have been the motives? Curiosity, the temptation to cultivate life beyond one's own cradle, the use of a planet as a biological testbed before attempting riskier colonization, or the deliberate spread of hardy life forms to sustain interstellar passengers. Each motive shapes different expectations. A civilization interested in biospheric engineering would favor organisms that could survive a wide range of chemistries, and that would modify local geochemistry in detectable ways, mineral precipitating microbes that consolidate sediment, organisms that alter redox gradients, or life that binds fine sediments into laminated structures. These biogenic fabrics are not monumentality in stone. They are distributed, collective architectures, ecosystems that build by accretion rather than by hammer and chisel. Such engineered biospheres, if buried quickly in deltas or protected by mineral matrices, are the kinds of traces most likely to survive deep time. More explicit forms of intervention complicate the picture further. Imagine probes designed to deliver genetic material, or machines constructed to prepare world-melting ice, mobilizing volatiles, seeding microbes in protected aquifers. Energetically, a small, autonomous craft could ferry material to Mars with far less delta V than reaching the outer planets. A civilization that was not indifferent to cost would favor lower energy hops. The engineering signatures of such operations would be subtle, anomalous isotopic ratios from industrial processes, localized enrichments of rare elements used in electronics or reactors, or physical disturbances in stratigraphy where landing and excavation occurred. Over billions of years, however, these signatures would be attenuated. Metals corrode, alloys oxidize, polymers depolymerize. Unless artifacts were rapidly buried in anoxic sediments or mineralized by groundwater, their survival prospects shrink dramatically. This is where preservation arithmetic becomes decisive. Deep time is an unforgiving filter. Cosmic rays and ultraviolet degradation over millions of years erode organic molecules. Impact gardening churns the upper regolith. Oxidation and perchlorates complicate chemical records. Yet burial within fine-grained sediments and encapsulation and mineral concretion dramatically increases longevity. The practical implication is stark. The most plausible relics of visitation, if any exist, are not towering statues on open plains, but subtle anomalies preserved in inner laminae, in concretions, in mineral veins. The search must therefore be ancillary to conventional geology, drill cores, micropetrography, isotopic assays, and the hunt for mineral fabrics incongruent with local geology. In short, a seeded or visited Mars would leave its best evidence in the places that geologists already prize, the quiet beds of ancient lakes and the deepest reaches of deltas. Another layer of interference arises from the chemistry of seeding itself. A deliberate act of seeding could leave isotopic fingerprints. Life, even engineered life, often prefers certain ratios of light and heavy isotopes. Biological fractionation produces patterns. Light carbon enrichment, specific sulfur isotopic anomalies that can be statistically distinguished from abiotic processes given sufficient context. A directed seeding that used terrestrial-like biochemistries might carry isotopic biases recognizable against the local inorganic baseline. But as compelling as that sounds, Isotopic signals are slippery. Abiotic processes can mimic biological fractionation under particular temperatures or redox conditions. Thus, the compelling case would be concordance across multiple lines: morphology, isotopic relationship, mineral context, and organic complexity, each reinforcing the hypothesis of intentional introduction. The notion that Mars served as a transit station, an orbital depot or logistical way station for interstellar voyages adds another set of expectations. Civilizations traveling through space need resources, volatile reservoirs, water for fuel and life support, stable infrastructure. Early Mars, with water and a thicker atmosphere, could serve as a refueling point. If this scenario holds, one might expect not biological seeding, but engineered manipulation of landscapes, excavation to create subsurface reservoirs, strategic placement of thermal systems to release volatiles, or even the relocation of rock to create landing pads. Evidence here would be at geological scales, anomalous depressions inconsistent with impact origin, patterned excavations within craters, or mineralogical disturbances associated with thermal alteration. Deep-time erosion again is the enemy, but some perturbations, large-scale rearrangements of mass or chemical reservoirs, might leave recoverable anomalies detectable by gravity mapping, subsurface radar, or careful stratigraphic mapping. Beyond empirical detection, the idea of visitation refracts profoundly on the human psyche. If Mars was intentionally seeded or used as a depot, questions of kinship cascade into scientific and philosophical worry. Life on Earth would no longer be an isolated experiment, but part of a larger chain of planetary manipulation. That possibility shifts the question of origins from the apocryphal to the ethical: who seeded whom and with what right? Would the discovery of engineered ancestry diminish human uniqueness, or would it expand the narrative of continuity across the cosmos? The emotional pitch is delicate. To some, the prospect offers consolation, a sense of connection to a broader biological project. To others, it imposes an unsettling sense of contingency. Human life becomes a derivative, a product of design rather than spontaneous emergence. Scientific caution tempers these emotions. The burden of proof under such hypotheses is high. Extraordinary claims require convergent, reproducible evidence. The protocol is as much philosophical as practical. Generate hypotheses about signatures, test them against null models of natural processes, and demand cross-disciplinary confirmation. The search strategies that naturally follow are measurable and specific. Orbital assets should map mineralogy at ever finer spectral resolutions, with an eye for isotopic proxies and unexpected elemental concentrations. Ground-penetrating radar and seismic surveys can prioritize targets with anomalous subsurface structure. Rovers and landers should drill into protected laminae, extract cores with contamination control, and seek isotopic and molecular patterns across stratigraphic sequences. The apex of this program is sample return, bringing Mars's deep-time archives into terrestrial laboratories where instrumentation can distinguish fine-grained isotopic and molecular signatures with orders of magnitude greater sensitivity than instruments constrained for spaceflight. There are, of course, reasons to be skeptical. The statistical likelihood that an external civilization would seed Mars, choose the same biochemical substrates that produce recognizable fractionations, and do so in a way that leaves unambiguous evidence after billions of years, is small. Parochial assumptions about what life looks like and how a civilization operates may bias expectations. Yet these considerations do not render the hypothesis useless. Instead, they reframe it as a productive constraint on exploration design. The hypothesis is valuable insofar as it suggests where to look and how to prioritize observations that would be informative. Under multiple scenarios, whether Mars hosted independent life, received life from elsewhere, or served as a technological depot, the motif of interference returns persistently. On Mars, natural and artificial processes would intersect: biofilms, precipitating minerals where a later landing dug trenches, impact ejecta, scattering fragments of a buried technological layer, volcanic ash, sealing a microbial mat into a protective shell. Each intersection complicates interpretation. The laboratory of Mars is a palimpsest whose ink runs together. Distinguishing a faint, deliberate inscription from the overlapping strokes of purely geological hand requires patience, precision, and humility. At the emotional center of the inquiry lies a simple human posture to listen. "Mars's strata do not shout," they whisper. The possibility that another intelligence touched the planet, whether by accident or design, is less a neat hypothesis than an invitation to enlarge a method. It nudges humanity to use its tools with a new humility, mindful of scale and attuned to the quiet places where preservation favors meaning over spectacle. Whether the verdict will be that Mars was a waypoint in an interstellar itinerary, a laboratory for alien experiments in ecology, or simply another world where chemistry nearly, but not quite, tipped into complexity remains unknown. What is already clear is that the search will be slow and subtle, a long forensic excavation of interference patterns written in stone and salt. In the ledger of the solar system, Mars may record not one story, but a conversation between processes, chance, chemistry, and perhaps choice. The task of decoding that conversation belongs to a species whose own tenure is vanishingly brief in the ledger's margins. That brevity should breed humility more than urgency. There is no immediate pressure to pronounce. Instead, there is a method: map broadly, probe deeply, and accept that the faintest anomalies require the most patient scrutiny. If, at the end of that work, the red planet reveals evidence of visitation, of intentional seeding, or logistical occupation, the revelation will not feel like conquest. It will feel like an accumulation of careful, corroborated understanding, a slow, rigorous answering of a question posed at the edge of human time. And even if the answer is silence, the endeavor itself will have taught something about how to listen to worlds older than memory, and about how small and temporary a single species is against the vast, indifferent backdrop of planetary history. What if the most radical possibility in the ledger of planetary histories were true? That Mars was not merely a neighbor, but once a cradle, that a mind had looked out from a red horizon and, facing planetary decline, chosen to leave? The idea lands like a sacramental question, both gravitational and destabilizing, because it rearranges the usual questions of habitability into a narrative of origin, migration, and memory. It asks more than whether life arose on Mars. It asks whether history itself might have been routed through that planet, whether the storylines of biology and culture could cross worlds. As a thought experiment, it is compact. As a scientific proposition, it is sprawling and insistently measurable. The work of testing it is the work of reconciling scale between deep time and the frailty of artifacts, between thermodynamics and cultural possibility. The first constraint is temporal and unforgiving. Mars's most clement epochs, as the geological record suggests, were concentrated early, the Noachian era, roughly 3.5 billion years ago. That window is substantial by many measures, hundreds of millions of years, but it must be read against the empiricism of biological tempos. On Earth, simple life appears remarkably early after planetary stabilization, but the climb from microbial mats to complex multicellularity and then to technological intelligence required billions of years, and a sequence of contingent events, eukaryogenesis, oxygenation, ecological interplay, whose timings are themselves the result of chance and planetary circumstance. If Mars hosted life during the Noachian, the question becomes probabilistic. Did Martian biology take evolutionary pathways fast enough or sufficiently different that a technological species could emerge within a compressed window? The mathematics of deep time does not forbid it. It simply requires extraordinary circumstances, accelerants that might alter evolutionary tempo. What could those accelerants be? The answer lies in the planet's heterogeneity. Hydrothermal systems concentrate chemical energy, confined basins preserve stable gradients, mineral interfaces catalyze complex chemistry. On a smaller planet, with more extreme local gradients and fewer ecological redundancies, selective pressures might favor rapid innovation. Sociality could be favored in cramped, resource-variable environments. Biomineralization could produce architectural permanence of a different sort. None of these pathways equates to certainty. They shift probabilities and open alternative narratives, biological civilizations that build with living matter rather than stone, social systems that prioritize information encoded chemically rather than in lithic monuments. The point is methodological. If the Mars was home, hypothesis is to be credible, it must be mapped onto concrete, testable mechanisms that could plausibly shorten or redirect evolutionary trajectories. The second constraint is preservation. Time is an indifferent archivist. Exposure on the Martian surface subjects organics and engineered materials to relentless radiation and chemical oxidation. Impact. Gardening churns the upper meters of regolith. Thermal cycling fractures. This arithmetic of decay means that anything left exposed on the surface tools, standing monuments, metallic machines, faces vanishingly small survival probabilities over billions of years unless protected. The most plausible preservational strategy is quick burial and mineral encapsulation. Materials trapped within deltaic mudstones, sealed in siliceous sinter, or incorporated into concretions gain a form of geological immunity. Radiation attenuates, oxidants are excluded, and delicate microtextures can be preserved. Thus, if a civilization on Mars existed and left traces, the argument of taphonomy pushes the search away from grand surface ruins and toward the quiet, buried histories the planet has retained, the innermost laminae of river deltas, hydrothermal deposits, and the mineralized veins of former aquifers. Migration mechanics, how any planetary people might have left, is the third axis of constraint. In the natural experiment of lithopanspermia, rocks ejected by impacts travel icy, missile-like across the void, and occasionally land softly enough to deliver surviving microbes. This process is stochastic and low bandwidth for the transfer of complex organized life, let alone technicians and artifacts. The survival probabilities for intact macroorganisms or complex organisms embedded in rock are effectively negligible across multi-million-year exposures. Therefore, if an exodus occurred, it most plausibly fell into two categories: a biological seeding life as cargo, or a technological departure, directed, engineered transfer of minds or machines. Directed migration presupposes technological capability, construction of craft capable of controlled atmospheric exit, interplanetary navigation, and soft landing on another world, the sorts of engineering steps humanity is only now approaching. Energetically, the barrier is high but not infinite. Mars's lower escape velocity and its position within the inner solar system reduce the delta-v penalty relative to interstellar hops. A civilization with advanced metallurgy, chemical mastery, and an understanding of propulsion could, within the realm of physics, engineer outward migration. The archaeological signature of such an endeavor, however, will be difficult to preserve. Launch facilities scoured by wind, refueling depots altered by oxidation, landing pads eroded by aeolian processes. Unless such infrastructure was rapidly buried or mineralized, it would leave scant trace. The most plausible remnants of engineered migration would therefore be anomalies in subsurface strata, sudden introductions of concentrated metals, isotopic irregularities associated with industrial chemistry, or dense, non-native alloys trapped in protected sediments. Biological seeding, intentional directed panspermia, creates a different set of expectations. If life was intentionally dispatched from Mars to another world, or vice versa, the evidence might be subtle but detectable: a shared molecular signature, an isotopic bias imprinted across independent phylogenies, or lithic records of deliberate containment strategies for microbial cargo. But even here the challenges are acute. Biochemical commonality between Earth and Mars could mean either shared ancestry or convergent chemistry. Distinguishing those possibilities requires not merely the presence of organics, but a chain of corroborative evidence, molecular complexity with distinct chirality or polymer structure, isotopic ratios incompatible with abiotic fractionation, and stratigraphic contexts that argue for exogenous introduction rather than indigenous formation. Where, then, should investigators look for signs that Mars might once have been a cradle and a launching point? The answer converges on habitats that combine potential for life with strong preservational promise. Ancient deltas like Jezero, long-lived lacustrine mudstones like those sampled by Curiosity in Gale Crater, silica-rich hydrothermal terraces, and sulfate concretions. These are the environments that are both most likely to have hosted complex chemistry and most likely to have locked away its record. The discovery calculus favors subsurface cores, microstructural petrography, and isotopic assays in terrestrial laboratories. The value of sample return becomes clear. Instruments on Earth are orders of magnitude more sensitive than those that can be packed into a rover, enabling the discrimination of subtle chemical and isotopic patterns that might betray a non-abiotic provenance. Meteorites, too, are part of the search strategy. Rocks flung from Mars to Earth provide a rare, tangible bridge. The controversial ALH 84001 meteorite illustrated the perils and potentials of this route. Structures initially read as microfossils sparked extravagantly different narratives and then settled into a more cautious consensus. The lesson is methodological. Extraordinary claims must be supported by the concatenation of independent measurements, morphology, geochemistry, and mineral context, each resisting plausible abiotic replicates. A Martian origin civilization hypothesis would demand even higher standards. If artifacts of biological signatures had been carried to Earth, they would most likely be irrevocably altered by terrestrial processes unless they were discovered embedded with an ancient, undisturbed strata dating to well before modern contamination. An alternative detection vector is the Moon. The lunar surface, with its minimal erosion and absence of atmosphere, is a far more forgiving preservation environment for things built or deposited in antiquity. If any technology left Mars for interplanetary or interstellar ambitions, the Moon might have been used as a depot or graveyard. The expectation would be very different. Without atmosphere, metallic artifacts and durable ceramics are protected from chemical weathering. A carefully targeted lunar survey, high-resolution imaging, subsurface radar, and in-situ analyses might reveal anomalies inconsistent with natural impact or volcanism. Such a discovery would not prove Martian origin, but would be a significant anomaly necessitating cross-checks with Martian stratigraphy and isotopic inventories. Beyond instruments and stratigraphic strategies, an intellectual barrier looms, distinguishing cultural narrative from scientific inference. The idea that Mars was a homeland resonates with cultural archetypes: the prodigal origin, the lost Eden, the Exodus. These archetypes can skew interpretation, encouraging pattern seeking where restraint is warranted. Scientific culture, in turn, has developed protocols precisely to dampen this bias: blind analyses, contamination control, reproducibility, and the insistence on convergent lines of evidence. The Mars was home hypothesis is thus a test case in epistemic humility. It demands extraordinary evidence because it would restructure the origin story of life in the inner solar system. There is, too, a poignant human dimension in contemplating such a scenario. The possibility that intelligence arose elsewhere and then left, or that life was carried from one world to another, reframes the meaning of survival and legacy. It suggests forms of disappearance that are not violent annihilation but patient erasure, the slow erasure that time imposes upon the most delicate archives. The pathos of vanished projects is a recurring human theme: cities swallowed by silt, cultures forgotten in deserts, languages unspoken again. A Martian exodus, if ever attested, would be the planetary scale echo of that smallness. It would be a record of ambition, intersecting with planetary fate, of engineering meeting entropy. All of this returns to a methodological imperative: convert speculation into a prioritized observational program that tightens the hypothesis' improbable knots. That program would include targeted drilling into the most promising lacustrine and deltaic deposits, the systematic analysis of returned cores for trace metal anomalies and isotopic discontinuities, renewed scrutiny of Martian meteorites with contamination-resistant methodologies, and lunar surveys designed to detect preserved, non-natural objects or assemblages. It would also expand comparative deep time studies on Earth, examining the oldest sedimentary packages for abrupt introductions of materials or isotopic anomalies that cannot be explained by terrestrial processes alone. The statistics matter. The rarer the proposed event, the more robust and repeated must be the lines of evidence. Finally, the question matters because it reframes the ethics of exploration. To pursue the possibility that Mars was once home is to accept a certain interpretive modesty. It requires acknowledging the limits of remote observation and prioritizing preservation and contamination control. If sampling strategies are to detect faint, ancient signals, they must protect them from modern intrusions. That realization shapes mission architecture: clean sampling, sealed caches, careful chain of custody, and an openness to protracted analysis on Earth. In the ledger of planetary possibilities, the thesis that Mars was once a cradle and a launching point is one of the loneliest hypotheses: grand in implication, narrow in probable survivability, and demanding in its evidentiary burden. Yet it is not outside scientific scrutiny. It can be parsed, parameterized, and tested by numbers, isotopic ratios, radiometric dates, depth of burial, energy budgets for launch, and the statistical likelihood of preservation. Those metrics do not diminish the idea's romance, they discipline it. To hold the hypothesis responsibly is to let wonder set the agenda for inquiry, and to let method be the arbiter of claim. The consequence of that posture is both practical and ethical. Practically, it channels resources toward the quiet places where planetary memory is most likely to be conserved. Ethically, it resists the temptation to convert longing into proclamation. Whether Mars was cradle, depot, or neither, the search for the answer is valuable. It stretches instruments, refines methodology, and deepens human humility before time. The ledger of Mars remains open. Each borehole, each returned core, each meteorite examined is a new line in a gradual accounting. The radical claim that a civilization once left the red world in order to survive poses a narrative challenge. It is a provocation that compels the advancing of tools and the patient reading of strata, because if such a story were true, its traces would be faint and buried, and the evidence would require the slow labor of many instruments and many years to bring to light. If not true, the search will still have yielded something no less important, a clearer map of how worlds remember, and how easily even the most ambitious acts of intelligence can be erased by the indifferent arithmetic of deep time. What if, amid the slow arithmetic of craters and dunes, there were also shards of something unmistakably artificial, metallic glints scattered along orbits and on wind-swept plains? What would it mean, not merely for curiosity, but for the logic humans use to read deep time, if pieces of engineered matter drifted through a planetary ledger otherwise dominated by rock and ice? The discovery of metal fragments and structural detritus in orbit and on the surface of Mars will be the kind of observation that rearranges how a species hears its own silence. It would not speak with the rhetorical finality of a carved monument. It would whisper through spectroscopy, radar echoes, and the statistical oddities of orbital mechanics. The whisper would still be powerful because engineered things, polished alloys, regular lattices, seams formed by bolts and welds are a different kind of record than sediments and minerals. They are evidence of intentional arrangement, a history of decisions translated into material form. The observations that could produce such a whisper arrive in many technical guises. From orbit, the first hints are not usually obvious, glints, but patterns in motion and reflectivity. A cluster of objects sharing nearly identical inclinations and eccentricities suggests a common progenitor, the breakup of a body that once moved coherently through space. Orbital mechanics is unforgiving and precise. When debris fans out from a parent object, its fragments trace the fingerprint of that ancestral orbit. Analysts on Earth used to sorting artificial fragmentation events in the Earth, Mars neighborhood, would look at orbital elements statistically. Is there a concentration of semi-major axes and inclinations around a mean value, or does the distribution mirror the random catalogue of captured meteorites? A non-random clustering is a red flag, one that insists on a generative event rather than a steady-state background. Spectroscopy then supplies the compositional layer. Metals have spectral signatures. Iron-nickel alloys, titanium alloys, and aluminum reflect sunlight and infrared in characteristic ways, and these reflections differ from the spectral slopes of basaltic rock or rusted iron oxide. Synthetic coatings, polymers, ceramics, paint residues carry their own fingerprints in ultraviolet fluorescence and near-infrared. Absorption bands, sensitive multispectral imagers aboard orbiters can separate out these signatures, especially when combined with photometric modeling that accounts for angle, roughness, and particle size. A sudden, localized spike in radar reflectivity or a thermal inertia anomaly where the ground retains heat differently than surrounding regolith strengthens the claim. A dense, non-porous inclusion stands where porous sediment should be. Yet, detection is only the beginning. Interpretation lives in the stubborn middle ground between plausible, natural explanations and the tantalizing alternative that some of these fragments are remains of a constructed object. Satellites, stations, or perhaps something older and stranger. Mars is not a blank slate. Iron meteorites fall there as they do on Earth. They can appear as bright, metallic boulders with high radar cross-sections and anomalous thermal behavior. Distinguishing a natural meteorite from a corroded leg of a machine requires context. The geological setting matters. A linear trail of fragments pointing downhill from a single disruption site suggests breakup in flight or an impact scattering. Isolated, morphologically regular plates embedded in layered sedimentary rocks suggest ancient burial and entombment rather than fresh fall. When debris is found in orbit, orbital lifetime and decay models become an essential clock. Around Earth, atmospheric drag shortens the lifetimes of low-orbit objects. Around Mars, the much thinner atmosphere produces very different dynamics. Low Mars orbits are less rapidly decayed by drag, but they are subject to perturbations from solar radiation pressure, third-body interactions, and the planet's oblateness. In practice, a coherent field of small orbital fragments could persist for millennia, even millions of years, if their orbits are stable enough and if they avoid destabilizing resonances. But millennia and millions are not billions, and the survival of delicate composite materials across deep time in orbit is improbable. Metals in vacuum resist chemical corrosion, but they do not resist being peppered by micrometeorites. Sun-driven sputtering that slowly erodes surfaces, and thermal cycling that induces embrittlement and fragmentation. Large, durable structural elements, thick titanium trusses, dense molten cast blocks, have a better chance at persistence. But even they will wear, fracture, and eventually tumble into new orbits or descend to the surface under cumulative perturbations. Surface finds tell another story altogether. In the arid, cold conditions that have governed much of Mars for billions of years, burial can preserve a piece of engineered metal embedded in a deltaic deposit, sealed by later sedimentation and capped by silica or sulfate minerals, could be shielded from radiation, from chemical oxidation at the surface, and from the ceaseless abrasion of wind-blown grit. In such context, the microstructure of a fragment, machined holes, alloy grain patterns, traces of machining coolant, weld seams with evidence of thermal profiles would survive far better than an exposed satellite leg tumbling on an empty plain. Radar and gravimetric anomalies can flag dense buried bodies. Ground-penetrating radar picks up contrasts and dielectric properties. A metallic mass stands out as a bright, coherent reflector. Gravity mapping can reveal small but measurable density anomalies when concentrated metals form a lens in the crust. If those two lines of evidence coincide, an anomalous radar reflector sitting in a gravity low or high. And if the stratigraphy surrounding the reflector dates to a period plausibly ancient, the odds of a non-geological origin rise. And yet each of these lines is porous to alternative explanations. And what? A gravimetric high might be a basaltic intrusion or a buried meteorite cache. A radar reflector might be a concretion, a cemented layer of evaporating minerals, or a buried lava tube. The patience of scientific method is necessary. No single anomaly suffices. Convergence is required. Morphology plus spectral identity plus contextual geology plus stratigraphic sequencing. That convergence is what separates a curious oddity from a claim of engineered origin. How would such fragments be dated? In situ radiometric techniques, argon-argon dating of enclosing igneous layers, cosmogenic nuclei dating of exposure, ages for surface fragments, and stratigraphic bracketing using crater counting provide temporal constraints. If a fragment resides in a layer between two datable horizons, its minimum age becomes robust. The presence of corrosion products, their mineralogy, and isotopic ratios can themselves be clocked. The formation of sulfates or chlorinated compounds follows pathways that depend on time and environmental chemistry, yielding indirect but informative age proxies. Where possible, return samples, open additional doors, laboratory mass spectrometry, microstructural electron microscopy, and trace contaminant analysis can reveal manufacturing residues incompatible with geological processes. Beyond the lab lies the interpretive landscape. What could these fragments represent? A conservative cascade of hypotheses begins with known human technology. The last 5 decades of Martian exploration have left an inventory: orbital platforms, landers, rovers. Rogue fragments on the surface or in orbit might be relics of robotic missions, micrometeoroid-stripped components, or accidental debris from terrestrial launch activities in the deep past. Their composition, isotopic signature of metals, and fabrication markers would match known terrestrial alloys and production techniques. If a fragment bears stainless steel with particular weld patterns or polymer laminates consistent with known human engineering, the case is straightforward. A more provocative hypothesis is that the fragments are the remains of an earlier, non-human technological presence, either an indigenous Martian industry, an alien visitation, or an even less intentional interference such as material transported from elsewhere. Here, the burden of proof increases. The composition of an anomalous object could be entirely unfamiliar. Complex alloys with elements and ratios not common in natural meteorites, non-terrestrial isotopic distributions, or polymeric structures with ordered repeating units unlike terrestrial organics. Even more telling would be patterns of assembly interlocking parts with serial regularity. Fastener arrays not explained by stress fracturing or coherent formwork in alloy sheets that match no known natural process. Still, caution is necessary. Crystal growth, columnar jointing, and evaporitic layering can mimic regularity at certain scales. Geometry, by itself, remains ambiguous. Orbital architecture provides another vector of analysis. Human-made satellite constellations display telltale orbital families, similar inclinations, phased positions, and coordinated east-west spacing. If debris fields around Mars show remnants of an organized orbital network, objects phased in, common resonances, clustering at particular longitudes, or aligned in similar eccentric rings, then the hypothesis of past telescopic networks for satellite arrays gains plausibility. Conversely, a random distribution favors natural origin or an ancient, chaotic breakup. There is also the possibility of structural remnants in particular landscapes that cannot be explained by simple erosion. Long linear ridges with internal, high-density cores, voids with geometric cross-sections detected by radar, or anomalous thermal behavior in craters. These are the sorts of signatures that command deeper inspection. Anomalies concentrated in sheltered locales beneath thick deltaic deposits within ancient hydrothermal systems under volcanic ash layers are especially tantalizing because those are the places where preservation is strongest. The very taphonomy that favored early life's archival burial in fine sediments, mineral encapsulation, low oxygen also favors the survival of manufactured objects. What would the human response be? Without invoking individual actors, the collective reaction is predictable in tone, if not in detail. The discovery of potential technological debris in orbit or on the ground would ignite a complex blend of wonder, skepticism, and methodical zeal. Institutional priorities would shift toward verification missions, with proposals to retask orbital assets for dedicated high-resolution mapping, to deploy radar-sounding passes over anomalies, and to plan targeted landings or sample return campaigns. The debate would be both scientific. What is the null hypothesis? How many independent lines of evidence are required? And philosophical. What do humans owe a planet that might carry the material traces of minds, whether alien or human? Ethical concerns would quickly assert themselves. The imperative to avoid contamination, both forward contamination of Mars by Earth life and backward contamination of Earth by returning samples, takes on new weight when engineered detritus is at stake. A fragment that is unequivocally artificial would be a cultural artifact of potentially enormous significance, and decisions about its handling, site protection, and eventual curation would be matters of global governance. The scenario would provoke questions about ownership, stewardship, and the unwitting rewriting of another world's history. The simple act of retrieval might erase contextual clues that remain readable in their in situ state. It would be a paradox. The desire to examine would risk altering the very record sought. Practicalities of retrieval are not trivial. Rendezvous in Mars orbit is a different class of challenge than sample return from the surface. Objects in low Martian orbit have velocities relative to potential interceptors, and their chaotic tumbling complicates capture. Grippers, nets, and containment designs would need to be adapted to unknown mass and spin states. Surface retrieval demands landings in rugged terrain or in regions where dust and regolith mobility threaten both instruments and samples. Moreover, the retrieval mission itself would be an act that writes a new line into Mars's ledger, the presence of another spacecraft. Its thruster plumes and the disturbance of regolith would be part of the palimpsest. Even absent retrieval, the mere distribution of fragments encodes narratives about the past. A belt of debris sharing orbital planes might be most parsimoniously explained by the breakup of an artificial satellite, an event that, in its own way, is a technological fossil. A scattering of metallic shards in the lee of a crater could be a crash site. A coherent subsurface reflector beneath a sedimentary basin could be a buried, shielded structural mass. Each pattern is not proof in isolation, but a clue in an accumulating detective story. There is also a broader temporal question. How long can a technological remnant persist as legible evidence? The rhythms of deep time answer with arithmetic. Exposure ages, sputtering rates, micrometeoroid flux, and orbital chaotic diffusion give order of magnitude constraints. The longer the suspected age, the more likely that only the densest, most geometrically robust components will survive with interpretable features. Polymers and thin sheet metals are ephemeral. Titanium trusses and massive alloy blocks are relatively more durable. The most plausible ancient artifacts are therefore those integrated into rock, cast into concretion, trapped in sinter, or entombed within sediment, where geologic processes both preserve and conceal. Ultimately, debris in orbit and on the surface functions as a bridge between imagination and method. It is a raw material for stories that reach back into deep time and forward into human decision-making. The presence of engineered fragments would not, on its own, resolve the larger questions about life, intelligence, or contact. It would, however, redirect attention away from surface spectacle and toward the subtle, buried, and orbital traces that best survive planetary vicissitudes. It would teach once more that the ledger of worlds is written not only in cliffs and dunes, but in the metal that endures, the cavities that conceal, and the orbits that remember motion long after the minds that made it have gone. In the end, the significance of scattered metal on Mars would be less a cathedral of proof than a prompt for patient archaeology on a planetary scale. The work would be incremental, demanding cross-disciplinary tools, orbital mechanics, spectroscopy, radar geophysics, material science, and careful taphonomy. It would require restraint, to publish only when converging lines of evidence have been weighed. to guard samples against contamination and to resist the temptation of premature narrative closure. The fragments themselves would remain mute, but their geometry and chemistry would open a conversation that bridges Earth and Mars, past and present, natural history and the possibilities of agency. In that conversation lies both the risk of projection and the reward of understanding, a chance to read the faint ink of technology in the margins of a planetary ledger, and, in doing so, to learn how worlds remember what we most want them to keep. What happens to a public story when the images meant to make a planet legible are, in places, made intentionally or accidentally illegible? The question is simple but corrosive. It feeds a peculiar human economy. The quieter a truth is kept, the louder the rumor that it conceals becomes. In the case of Mars, the red ledger of rocks, salts, and long-buried lakes, the treatment of visual and contextual data has become a fault line. Photographs arrive with blur and noise, metadata fields appear emptied or scrubbed, and sometimes high-resolution frames do not hit public servers for months or years. To an attentive public, this pattern looks less like a technical footnote and more like a story. That's something, some answer, some piece of evidence is being withheld, viewed without preconception. There are many, often mundane reasons. Imagery and metadata do not appear cleanly in an archive. Spacecraft are instruments of immense complexity, streaming bits across millions of kilometers. They sample scenes at rates that exceed the ability of a distant ground station to record them in one pass. Bandwidth is an economy. Raw frames, often tens or hundreds of megabytes, must be compressed, prioritized, and sometimes truncated. Onboard instruments employ data compression algorithms that trade fidelity for survivability. Packets can be lost in solar conjunctions or during deep space transmission glitches. Images that arrive with missing lines, smeared pixels, or shifted headers are not conspiracies so much as the arithmetic of a distant sensor fighting to be heard. There are also institutional practices that shape the public palate. Mission teams typically follow protocols for calibration and validation. A high-resolution camera returns a raw file. That file then goes through a pipeline, radiometric correction, flat fielding, distriping to remove readout artifacts, geometric rectification against orbital ephemerides, and mosaicing where many frames must be stitched into a continuous map. Each step improves scientific utility, but also transforms the original pixel array. Metadata timestamps, spacecraft attitude, instrument temperature, camera gain settings are maintained in parallel files. At times, a missynchronization of those ancillary records can produce a public image with incomplete or missing metadata, not because someone chose to hide the context, but because the pipeline was interrupted, corrupted, or simply deprioritized. And yet technical explanation is not the whole story. There are legitimate, sometimes legal reasons for delayed or redacted release. Early in a mission, scientists and engineers are afforded a period of exclusive access so that the team that designed and operates the instrument can validate and interpret the data. This embargo is a kind of social contract. The field advances best when instrument builders can refine calibrations before 1,000 curious eyes reanalyze the same pixel and raise thrice the confounding questions. There are also security-related exceptions. High-resolution orbital imagery can reveal terrestrial launch sites, sensitive ground stations, or dual-use hardware if cross-referenced with Earth-side assets. Agencies sometimes redact or delay distribution for national security or diplomatic reasons or to comply with international agreements. In such cases, an image withheld for months may be withheld for reasons far removed from the matter of Martian archaeology. Planetary protection policy introduces another vector of restraint. The need to avoid forward contamination transporting Earth microbes to another world shapes not only the conduct of landing missions, but also how certain findings are handled. If a dataset hints at a potential biosignature that could be compromised by premature dissemination or that compels urgent protocols for sample handling, an agency may choose a cautious path. That path looks, to an outside observer, like secrecy. It looks like a door closed around a rumor that insists on flourishing. Where the situation grows clinical and political is where these operational and ethical constraints intersect with the sociology of information. Scientific institutions are not monoliths. They are networks of people under pressures, funding cycles, peer review incentives, public expectations, and the relentless drive to be first. The temptation to tease release, to drip-feed images that provoke but do not explain, is real. Slow, curated disclosure can be a strategy meant to manage confirmation bias and to prevent premature claims. But from the vantage of an anxious public, it has the opposite effect. It trains attention on what is being withheld rather than on what is supplied. The removal or obfuscation of metadata is particularly inflammatory. Metadata is the context that transforms a pretty picture into a datum, the exposure time, the spacecraft's position and pointing, the instrument's gain and offset, the filter band used, the time within the diurnal cycle. Without it, an image becomes a puzzle with holes, easy fodder for conjecture. To those who believe something is being concealed, the empty fields are a proof, because metadata are the key to verifying or falsifying extraordinary claims. An image without geolocation is a locked postcard. The instinct to demand a key to insist that raw files and unaltered headers be published is not merely paranoia. It is a call for reproducibility, for the ability of a community outside the mission to rerun the corrections and ask independent questions. There are also more prosaic, but no less consequential, technical habits that foster mistrust. Image processing techniques designed to remove instrument artifacts sometimes introduce patterns that the eye reads as structure. Deconvolution, used to sharpen images blurred by imperfect optics, can create ringing artifacts or enhance noise into apparent edges. Compression algorithms, particularly lossy ones, can introduce blockiness and banding that mimic rectilinear geometry. When activists, enthusiasts, or well-meaning journalists encounter these artifacts absent the metadata describing the processing chain, they see pattern and assign agency. The image, in effect, begins to argue for itself, and the scientific reply that the details of processing are available and that different pipelines yield different outputs often arrives too late. The cultural dynamics that follow such episodes are predictable. Social media amplifies anomalies. A single processed mosaic can be screenshot, cropped, annotated, and reposted thousands of times within hours. Pattern seeking thrives in the ecosystem of likes and retweets. A blurred ridge transforms overnight into an emblem. Commentary accelerates into narrative. Once the internet has fixed an image to a story face, pyramid, runway! No subsequent correction fully reverses the cognitive momentum. The human mind prefers a tidy tale to the messy arithmetic of deconvolution curves and calibration constants. It prefers personalities to provenance. This is not to say that all concern is unjustified. There have been historical lapses, lost tapes, corrupted datasets, and institutional decisions that, in hindsight, fueled suspicion. Old magnetic tapes, once the standard media for storing high-volume raw telemetry, proved fragile. Records misplaced or mislabeled can appear as deliberate omission by the lights of a later generation. Archival practices evolve. An image that was stored in a lab's proprietary directory in the 1990s may not have migrated cleanly into modern public repositories. The absence of old metadata is sometimes an archival failure, an accident of human memory, and the obsolescence of storage formats. The cultural reading of that failure tends to be harsher than the mechanic reality. There is also the international dimension. Multiple agencies operate in overlapping orbits. Images from one orbiter may be redacted because of agreements with another agency, because of pending cooperative publications, or because of national export controls. The coordination required to publish a high-resolution mosaic assembled from assets across organizations is non-trivial. Each partner has a legal and ethical framework. The burden of harmonizing those frameworks can produce delay, and delay becomes, in the public imagination, evidence of concealment. Against these technical and institutional explanations stands the enduring psychological fact: secrecy breeds stories. The human mind is built to seek agency in the face of ambiguity. Anomalies in the record blur, missing timestamps, unexplained embargoes constitute invitations to narrative. They become the scaffolding upon which many construct the notion that some truth lies behind a veil. That truth may be old life. Modern artifacts are nothing but a pile of uninteresting rock. The form of the belief, however, has sociological consequences. It shapes how communities mobilize, how they lobby for transparency, and how they challenge institutions. The response from the scientific community has taken several pragmatic shapes. First, there is a growing insistence on openness by default. Agencies have expanded their open data initiatives, pushing to release raw files alongside processed products and to publish the processing recipes, every calibration step documented and archived. The intent is to make reproducibility an automated part of the data lifecycle. Raw bytes deposited into curated archives, checksum, validated, and paired with versioned processing code. It is a technical fix with philosophical ambition, to make the system self-correcting, to convert suspicion into verifiable steps. Second is the embrace of provenance metadata. Modern data standards recognize that a file is only as trustworthy as its chain of custody record. Provenance includes not only the instrument settings, but also the software versions used to process the image, time and operator of each processing pass, and even the hardware identifiers for calibration targets. Publishing provenance is a kind of ritual of accountability. It allows external parties to replicate the pipeline and test whether sharpening created an artifact or whether lost packets produced an irrecoverable gap. Third, there are new tools for public engagement that do not condescend to curiosity. Citizen science platforms enable independent reprocessing. They invite enthusiasts to run alternative deconvolution algorithms, to compare signal to noise across filter bands, and to test hypotheses about pattern formation using robust statistical tools. When the public can run their own pipelines, suspicion diffuses into shared work. The problem, one of access and literacy, remains, but the model shifts from being told the truth toward doing the labor of verification collectively. Fourth, agencies have adopted explicit policies about the release of high-resolution imagery of potentially sensitive targets, where preservation and protection are at stake, grave-like Apollo sites, for instance, or the coordinates of potential astrobiological finds. Agencies may coordinate to withhold precise geolocation to prevent contamination or vandalism. The rationale is ecological and ethical rather than conspiratorial. Protecting a fragile deposit from the well-meaning but biologically reckless behavior of tourists is a practical conservation, ethically planetary. Even with these constructive responses, the cultural seam remains. The narrative economy of suspicion tends to convert technical discretion into a story about a cosmic cover-up. That conversion, in turn, influences research priorities. Scientists feel an added pressure to anticipate sensational claims and build data products that preempt misreadings, annotated mosaics, layered visualizations that show raw and processed images side by side, and explanatory materials that highlight the pitfalls of pattern recognition in noisy environments. The ideal is not to do away with mystery. The deep time drama thrives on surprise, but to render mystery responsibly with the tools that let the public understand not just what is seen, but how it was made visible. There is a deeper philosophical lesson here, one that folds back into the larger meditation of the red planet as a ledger. Deep time erases. Preservation favors particular contexts and taphonomies. The more spectacular a claim about ancient intelligence or preserved artifacts, the more demanding the standards of evidence must be. Blur and missing metadata are, in the rhetoric of a fragile audience, the void into which the urgent question, what was once here, falls. That void is not merely procedural, it is existential. It reflects an anxiety about erasure and about whether some truths are being reserved, perhaps wisely, for careful adjudication, or whether they are simply beyond the purview of contemporary instruments, lost to the slow arithmetic of cosmic erosion. In the end, the politics of image handling, the sociology of release, and the mechanics of data pipelines are all part of the same story, a story about the interface between human curiosity and the limits of instruments. The reasonable path forward is not censorship nor unfettered release alone, but a calibrated openness that recognizes both the fragility of planetary contexts and the public's legitimate demand for reproducibility. That means publishing raw data with provenance, documenting every processing step, making calibration and deconvolution tools available, and protecting sites when preservation requires it. It also means educating audiences about how pixels become evidence, about the compression of a distant bit stream and the ethical choices behind an embargo. If people sometimes whisper that agencies keep images deliberately blurred, they reveal less about the motives of a few bureaucrats than about the broader human hunger not to be alone in time. The temptation to find company, monuments, faces, metal fragments on a world so old and mute is profound. The engineering answer is patient. Reprocess the pixels, read the headers, release the provenance. The cultural answer is gentler. Accept that silence can be meaningful and that absence of easy, dramatic proof does not diminish the value of exploration. The ledger of Mars will continue to accept entries, images, spectra, cores. The responsibility of those who write and release those entries is to make the text as legible as possible so that the public can read the planet not merely as a surface of sensational hints, but as a deep archive whose whispers can be amplified only through transparency, patience, and rigorous method. 10. The sudden disappearance. What would the ledger tell if one page ended not by slow fading but by a single violent blot? The question is small and surgical. If there ever had been a flourishing network of habitations, technologies, or living tapestries on a world, what would it look like if it was erased almost overnight by a blow so abrupt that its signature, in stone, is a sharp, unmistakable cut. This is not merely an exercise in imagination. It is a forensic problem, framed by physics and by the cruel arithmetic of deep time. It asks what kinds of endings leave clear marks and which dissolve into the soft blur of erosion and entropy. There are at least two broad families of endings to consider: instantaneous catastrophes and protracted collapses. Each writes a distinctive hand in the geology, and each leaves different prospects for retrieving a readable record millions or billions of years later. Instantaneous catastrophes are dramatic and relatively simple to model. A basin stripping impact of the kind that formed the largest basins in the inner solar system is a blunt instrument. The shock wave produces melt sheets, blast spherules, shocked minerals, and a global or regional layer of ejecta that can be dated and correlated. It also vaporizes and lofts atmosphere, pulverizes surface materials, and can sterilize exposed ecosystems. In the rock record, such an event appears as a sudden stratigraphic boundary, curtailed sedimentation, a distinct spike of exotic materials, spherules, shocked quartz, iridium or other siderophile enrichments, and a thermal pulse that alters nearby mineralogy. If a civilization left obvious, exposed monuments, many would be physically destroyed or buried by ejecta. The chance of survival hinges on depth and luck. Artifacts buried meters to tens of meters below the level of vaporized excavation have a chance to remain intact, things standing. In the open, do not. Another abrupt mechanism is a cosmic radiation event, a gamma-ray burst or a nearby supernova. The physics here is less about reshaping landscapes than about irradiating biology. A burst of intense high-energy photons could strip atmospheres and massively alter surface chemistry, producing oxidation events and sterilization, especially at the surface and in shallow subsurface layers. Its geological signature is subtle isotopic anomalies in noble gases, changes in cosmogenic nuclide abundances, a shift in production rates of certain isotopes preserved in mineral matrices. Detecting such a fingerprint across deep time is hard but not impossible. It requires precise, targeted isotopic work on materials that have remained closed systems since the event, minerals whose isotopic clocks were not later reset. Catastrophic volcanism and global-scale climate collapse form a separate class of fast endings with terrestrial analogues. A period of runaway volcanism, massive flood basalt events, floods a world with gases and ash. The atmosphere thickens with particulates, surface sunlight is attenuated, temperatures swing drastically, and acidification of waters can occur. Volcanic deposit layers, widespread ash beds, and abrupt shifts in sedimentary facies mark these intervals. Geochemically, sudden rises in sulfur species, spikes in certain trace elements, and dramatic changes in organic carbon preservation can indicate a rapid environmental upheaval. Again, the survival odds for artifacts depend on burial. Rapid ashfall can both obliterate and unexpectedly preserve, cementing things into a sealed layer that later becomes an archival snapshot. And there are endings whose violence is technological, a civilization's own instruments turned inward. Human minds can conceive of scenarios that are terrifyingly efficient, runaway engineered pathogens, self-replicating nanomaterials that consume specific substrates, industrial-scale environmental collapse, or warfare that harnesses energetic technologies with planetary reach. The hypothetical signatures of such ends are complex and, in some ways, ambiguous. A global industrial die-off could leave chemical residues, unusual concentrations of noble metals, synthetic isotopes, plastics turned into microglassy residues, or anomalous elemental ratios inconsistent with known abiotic processes. Plastics and complex polymers are fragile on geological timescales. They break into charred residues, cross-linked residues, or amorphous carbon. Metals corrode and redistribute. Yet, in certain mineralizing contexts, within anoxic sediments, within silica-rich sinters, or encased in evaporitic salts, these materials could be mineral stabilized and thus detectable, albeit degraded. A crucial analytical insight is that different extinction mechanisms distribute their signatures spatially and chemically in diagnostic ways. Impacts produce broad, synchronous ejecta, blankets. Volcanism leaves layers of ash and flood lavas. Radiation events change. Isotopic inventories, industrial collapse scours landscapes with chemical anomalies. But these anomalies may be local and patchy unless the industry was truly global. For investigators reading a planetary ledger, these distinctions are vital. They are the difference between a plausible hypothesis and speculative fiction. There is also an important temporal nuance. Rapidity is relative. A sudden disappearance that unfolds over hundreds to thousands of years can be functionally instantaneous in the geological. Record a clean break in sedimentation, or a sharp change in pollen, organics, or isotopes. Slow collapses that stretch over millions of years fade into background noise, their endpoints unreadable as discrete events. The detectability of any catastrophic end is therefore framed by the coarseness of geological resolution. The thicker the layer that preserves change, the harder to time constrain to human-like durations. Consider the emotional and existential implications for a species trying to make sense of such an erasure. The human reaction, if such a civilization existed and then vanished, is twofold. On the one hand, there is the clinical curiosity, the desire to reconstruct cause from consequence, to convert stratigraphic irregularity into causal chains. On the other hand, there is a darker, more intimate anxiety, the fear that endings can be sudden, that complex organization is fragile, and that the same physical or socio-technical vulnerabilities could mirror back onto any species capable of reflection. These are not merely rhetorical flourishes. The thought that a planetary scale experiment in organization could be extinguished in the span of a geological heartbeat presses on the collective mind. It reframes the ledger not simply as an archive, but as a set of warnings, possible exemplars of failure modes. That emotional economy propels science. It is both a motivation to search and a cautionary companion to interpretation. Detection strategies, therefore, must be both precise and plural. An investigator seeking signs of sudden collapse would combine stratigraphy, petrology, and isotope geochemistry with remote sensing and subsurface probing. They would look for abrupt terminations in sedimentation sequences, delta tops abruptly truncated, lacustrine beds sealed by a sudden influx of ash or blasts. They would examine any spheral layers for shocked minerals and high-pressure polymorphs. They would seek isotopic anomalies in noble gases, carbon, sulfur, and other elements that indicate mass fractionation or sudden alteration. They would model global distributions of ejecta and compare them to anomalous chemical horizons. Crucially, they would demand convergence. A single anomalous spike is not sufficient. Multiple, independent lines of evidence are necessary to elevate a cause from plausible to compelling. There is also an epistemic humility to preserve. The absence of an obvious catastrophic horizon does not prove the absence of a sudden end. Deep time is adept at erasing edges. Ejecta layers can be reworked, ash beds can be lens-shaped and localized, chemical anomalies can be obscured by later fluids. A civilization could vanish without leaving a global, unambiguous marker if its disappearance was punctuated by localized destruction, if its materials were biodegradable in geological contexts, or if the planet's post-event processes redistributed and obscured the signatures. Conversely, a localized natural catastrophe, an impact that sterilized a region, might mimic the aftermath of a global technological collapse in certain datasets if sampling is spatially constrained. These ambiguities yield an impetus not for sensational leaps, but for methodical programs. Search strategies prioritize places where preservation is highest, fine-grained lacustrine mudstones that can entomb organics, deltaic interiors that rapidly bury materials, silica sinters that fossilize textures, and subsurface aquifers where radiation and oxidants are attenuated. They push instrument development towards sensitive isotope ratio, mass spectrometers, deeper drilling capabilities, and non-invasive radar and gravity surveys capable of detecting buried anomalies. They insist on sample return for the highest stakes inquiries because Earth laboratories magnify analytical sensitivity by orders of magnitude. Finally, the question of sudden disappearance carries a cultural valence. The human imagination is drawn to endings, cataclysmic and decisive. Myths proliferate around sudden floods and fiery skies. When investigators read a stratigraphic cut that looks abrupt, the temptation is to link it to narrative closure. Science must resist that narrative greed. They must practice a discipline of agnosticism, to collect, to test, and to withhold final verdicts until patterns coalesce. The ledger of a world will tell what it can at its own pace. The silence after a possible sudden end is not merely the trace of absence, it is the call to patient, convergent inquiry. 11. The link with myth. How do stories, oral threads woven across generations, become a secondary archive of planetary events? In the human record, words have already proved stubborn: oceanic floods, volcanic winters, meteoritic catastrophes, and sudden climate shifts have vegetated the imaginations of peoples and become codified as myth. The link between myth and material history is not straightforward, but neither is it negligible. myth operates as a form of compressed memory, a social technology for transmitting information about hazards, resources, and moral lessons. If a dramatic event ever happened on a planet, impact, deluge, skyfire, or long eclipse, there is an a priori plausibility that cultures would encode it in narrative, ritual, and symbol. The pressing question for the planetary detective is how to use such cultural traces, measured in centuries or millennia, to guide a search across millions or billions of years. First, myths tend to be local and persistent. Flood stories, for example, crop up in many cultures because floods are relatively common, memorable, and disruptive events. In the archaeological record, flood myths have sometimes correlated with real inundation episodes, river avulsions, coastal transgressions, or tsunamis whose memory could survive across many generations. But the half-life of oral memory is not geological. Myths rarely survive intact for more than tens of thousands of years with reliable fidelity. This temporal constraint matters. It limits the set of events myths can plausibly recall. The Noachian epochs discussed earlier are orders of magnitude older than the maximum plausible endurance of oral tradition. Thus, while a myth may encode the memory of a cataclysm that hit thousands of years ago, it cannot reliably be taken as a direct witness to events billions of years old. That said, myths can be surprisingly conservative in form. Certain motifs, skyfire, a night without stars, prolonged cold, an endless storm, are evocative of specific physical phenomena. Bolide air bursts and impacts, magnetospheric collapse and spectacular auroral displays, volcanic winters and sulfate aerosols, prolonged atmospheric dust loading. Myths that congregate around unusual cosmological events may therefore still be useful as heuristic signposts. A concentrated cluster of myths describing a dark day when the sun went out across communities in a circumscribed region could indicate a volcanic or impact winter in the archaeological horizon. The job of scientists is therefore one of careful triangulation, match motifs to plausible physical processes, date the archaeological horizons associated with the myths, and then search for material signatures that corroborate a catastrophe at the assigned time. There is also the possibility that myths perform a preservational function of their own. They guide human attention to particular landscapes. Place names, ritual sites, and taboo zones sometimes protect locations that carry a geological memory. An oral tradition that insists a certain valley is haunted because stones fell from the sky may deter settlement and thereby preserve impact heights or unusual lithologies in situ longer than in more exploited regions. Ethnographic records show that sacred groves and taboo zones occasionally coincide with ecological anomalies, old-growth forests, springs, or unusual geological features. For an investigator, local knowledge can be invaluable. Communities living with the land often preserve ecological and geological knowledge in a form that can point expeditions toward unusual rocks, anomalous sediments, or mythic topographies worthy of study. But myths can also mislead. They are interpretive frames shaped by culture and metaphysics, not photographic records. A volcanic eruption can morph into a tale of divine anger. A meteor airburst can become the judgment of gods. That semiotic transformation is not deception. It is how human societies make sense of danger. For a scientist, the methodological demand is to separate the kernel, the event, from the shell. The cultural reinterpretation, comparative folklore offers tools here. Similar motifs appearing across disparate cultures, mapped against plausible geophysical drivers and archaeological horizons, strengthen the case for an underlying common event or process. Isolated stories, or those too rich in symbolic elaboration, are weaker evidentiary anchors. There is also an ethical caution. Modern investigators are a new generation entering landscapes charged with living human memory. Interpreting myths as clues must be done with respect and care. Extricating a sedimentary core from a place considered sacred can be a form of violence. Partnering with local communities, acknowledging their custodianship of stories and landscapes, and co-designing research agendas is not only ethical, it is pragmatic. Those communities hold knowledge, place names, ritual calendars, oral genealogies that can crucially refine search parameters. At a deeper level, the linkage of myth to possible bygone civilizations or to startling cosmic events speaks to the human propensity to saturate absence with meaning. Myths often do for the social imagination what archaeology does for the physical record. They construct narratives to explain the unexplainable. The psychologist's term pareidolia has its cultural analog, narrative pareidolia, the reflex to find coherent plot where only fragmentary evidence exists. Scientists must adopt a double humility: humility before the power of cultural memory, and humility about the limits of what that memory can reveal in deep time. Yet myths are not mere decoration. They can be engines of discovery. There are concrete precedents where local tradition led to geological insights. Elders' recollections of a great storm helped geologists locate ancient tsunami deposits. Oral histories of luminous skies helped astronomers correlate tree-ring spikes of radiocarbon with historical auroral observations. The methodology that emerges is interdisciplinary. Folklore specialists and anthropologists sit beside geochemists and remote sensing experts. Together they build hypotheses that are culturally informed and physically testable. The science becomes a conversation with memory, not an extraction of values. Finally, there is a philosophical dimension that ties back to the ledger. Myths are a species' attempt to purchase continuity in a world of erasure. They are cultural strategies for linking past to present, for making meaning out of disappearance. If a civilization vanished abruptly or gradually, then myths are the last best chance of its echoes persisting across human scales. But the cadence of myth is different from the cadence of stone. A myth can preserve the emotional truth of a catastrophe, a feeling of cosmic abandonment, the image of a sky that burned even when the material traces have been swallowed by time. For scientists, the practical lesson is modest and generous. Treat myth as a complementary archive. Use it to prioritize sites and to frame hypotheses, but demand geochemical and stratigraphic corroboration. Recognize that myth often points to the humanly significant, not the globally diagnostic. Remember that the planet keeps its own ledger: rocks, isotopes, impact spherules, and that stories are a bridge between human perception and those silent records. Together, folklore and geology form a methodological partnership. Each compensates for the weakness of the other. Stories remember what the stratigraphic column forgets, and the stones record what stories transform. In the interplay between sudden disappearance and myth, a broader truth emerges. Loss is not an endpoint, but an invitation to inquiry. Whether the cause is an asteroid, a volcanic winter, technological self-destruction, or nothing more than the patient erasure of weather and radiation, the act of asking, of listening to both rock and story, remains one of humanity's central practices. The ledger awaits. The investigator's task is to read it with precision, to consult the local archivists of memory, and to resist the siren call of premature certainty. In that restraint, there is a different kind of narrative power, the long, careful accumulation of evidence that, in time, can make absence speak with a clarity that honors both the silence of worlds and the voices that remember. What is a myth but a compressed form of attention, an economy of memory that a culture invents to hold fast to what matters and to warn against what was terrible? The question is the proper hinge for this chapter, a small, sharp idea that opens a long conversation. Across millennia, human communities have watched the heavens and told stories about what they saw. In the languages of Egypt, Sumer, the Maya, and many others, a recurring figure appears, a god or omen associated with redness, with war, with pestilence, with arrival from the heavens. The coincidence is striking on the face of it. Mars, the red planet, has been a conspicuous wanderer in the night sky since before human eyes learned to chart the seasons. Did those ancient references point to faint historical contact, some remnant of a bygone presence on Mars, or are they instead the human mind at work, transforming brilliant, disturbing lights into meaningful narratives? The narrator of cosmological inquiry must keep two stances simultaneously: a generosity to human imagination and an insistence on evidentiary discipline. The two do not contradict, they refine one another. On the one hand, myths are not merely idle fancies. They are social technologies for encoding memory, danger, identity, and sometimes empirical information about recurring phenomena: floods, comets, seasonal drought. On the other hand, oral and mythic traditions attenuate with time. Centuries compress motifs, millennia recast them, deep time erases them altogether. The methodological task, then, is to ask, what exactly could ancient peoples plausibly have remembered about Mars? And how might those memories have become myth without implying literal contact? The first, empirical observation, is simple and deserves emphasis. Mars is red. Its hue is a visual provocation. Across cultures, the color red carries resonance: blood, sun, fury, and soil. A visible star that gleams red at opposition, because of iron-rich dust scattering sunlight, naturally invites metaphorical association with war, with plague, with gods who strike swiftly and violently. The Sumerian Babylonian tradition exemplifies this process. In Mesopotamian astral theology, Mars is associated with Nergal, a deity of war, plague, and the underworld. Astronomers in the ancient Near East tracked the position and retrograde wanderings of the wandering stars with precision, and the behavior of Mars, its periodic brightening, its retrograde loop across the zodiac, lent itself to portentous readings. Those cultures wrote the planet into a moral grammar of omens. An unusually bright opposition or an anomalous retrograde could be read as an omen for kings and cities. Across the deserts of Egypt, the relationship between celestial observation and ritual life was similarly intimate. Although the interpretive idioms differed, the elite possessed instruments of observation knowledge embedded in temples and in calendars, and crafted myths that folded astronomical regularities into genealogies of gods and kings. Likewise, in Mesoamerica, elite scribes and priests were celestial technicians. They tracked the planets, recorded cycles, and linked planetary conjunctions to ritual calendars. The details vary culturally, but a common logic emerges. Bright planets do things in the sky. Humans read those things as meaningful because they matter to harvest, war, and survival. To translate these social processes into a testable hypothesis about memory, about faint recollections of Mars not as a poetic emblem, but as an actor that once arrived on Earth, demands several layered arguments. First, could a material event tied to Mars have occurred within the span of human history, one whose sensory footprint might be encoded in myth? Second, could that event plausibly produce the kinds of cultural motifs we find? Third, can the material record corroborate any suggested correlation? These are not rhetorical moves. They are the map of what must be measured. The simplest pathway by which Mars could leave a material trace on Earth in human time involves rocks. Meteorites from Mars do fall to Earth. Their provenance is established by trapped gas signatures matching what orbiters have. Measured in the Martian atmosphere, and fragments of Mars occasionally arrive on Earth as the most remarkable postcards from another world. For a pre-industrial community, an iron or stony object whose interior revealed minerals and textures unlike local stone would be astonishing. In some cases, those rocks were worked, revered, or buried as relics. A well-known example from Egypt is the iron dagger buried with Tutankhamun. Its alloy composition is consistent with meteoritic iron. That dagger was not an elaborated narrative of an emissary from the Red Planet, but it is emblematic of the way extraordinary physical objects from the sky could catalyze stories of divine origin. Meteorites are not, however, proofs of visitation. Most meteoritic material originates in the asteroid belt, and Martian meteorites are very rare. Yet a speck of rock from Mars or from any celestial body can still sear a symbol into local consciousness. The presence of meteoritic iron in cultural context helps explain why many societies attributed meaning to stones from the sky. It does not explain why myths singled out Mars repeatedly across geographically distant cultures. For that, one must examine cosmological salience rather than singular artifacts. A more plausible route is astronomical choreography, moments when Mars's appearance in the sky coincided with terrestrial calamity. If a particularly bright or unusual apparition of Mars occurred alongside famine, epidemic, or warfare, cultures predisposed to omen reading could weave the red planet into stories of descent and divine visitation. Retrocalculation of planetary positions allows modern astronomers to reconstruct the sky for any given epoch. Archaeoastronomers ask whether famous historical disasters cluster temporally with remarkable Martian apparitions. The method is precise. Generate ephemerides. Search historical texts and archaeological horizons for correlated events. Evaluate statistical significance. When correlations do exist, the hypothesis that a cultural myth was directly seeded by a memorable conjunction becomes testable. Another dimension, often overlooked, is the replicative power of metaphor in political theology. Rulers have sought celestial legitimation for as long as power has required an aura of inevitability. A king who can claim descent from a red star, or whose martial victories coincide with Mars's motion, acquires a cosmogonical imprimatur. Myth-making, in those contexts, is as much a technology of governance as it is a memory. The prevalence of gods from the red star motifs may therefore reflect the intersection of material spectacle, planetary brightness, social needs, legitimating power, and the elasticity of myth as propaganda. If a scholar seeks to adjudicate between legend and faint memory, the tools are interdisciplinary comparative mythology, isotope geochemistry, archaeoastronomical reconstruction, and contextual archaeology. Comparative mythologists map motifs across regions, seeking the structure of narratives and their possible diffusion routes. Do motifs of red descent cluster in time and space, or are they independent, local inventions that exploit a common perceptual cue? Linguists can track the spread of loanwords and ritual forms if a distinctive story about a red messenger migrates with identifiable material culture, pottery styles, metallurgy techniques, then diffusion is suggestive. But diffusion is not proof of extraterrestrial contact. It is proof of human contact and narrative mobility. Material science supplies a different kind of standing. If an ancient material deposit, an altar, a tomb, a metallurgical slag retains isotopic anomalies or element ratios that cannot be explained by known terrestrial processes, then the argument changes. A sample containing isotopic ratios consistent with non-terrestrial formation pathways or alloys with element concentrations unmatched in local geology must be explained. That is why a conservative, empirical route forward insists on what was suggested earlier: sample return, high-precision isotope work, and drill cores from the most preservationally favorable settings. If myths point to place, an island, a crater, a fallen mountain, then those places are survey priorities. The pairing of narrative and strata is the archaeologist's most promising tactic. But the narrator must also be clear about limits. Oral traditions have lifespans measured in generations, while motifs can persist in durable ritual forms, sacred sites, taboos, place names. The fidelity of an oral report to a given physical event diminishes with time. A myth might carry the emotional residue of a catastrophic cosmic event, a blazing sky, a long, cold winter, without preserving technical detail about origins. In other words, myths may be reliable reporters of subjective experience rather than objective provenance. That is itself a form of evidence. When many disparate communities retain a shared motif that describes a spectacular sky event, the likelihood increases that something extraordinary happened in the sky and left cultural traces. A final, necessary caution is the perennial danger of narrative pareidolia. Humans find agency where none exists because agency matters to social life. The desire to discover in myth a real Mars origin tale is a modern projection. It is a yearning, legible and instructive, but it is not a substitute for data. The method must resist the seduction of tidy stories. The appropriate posture is one of disciplined curiosity, to follow leads that myths provide, to test them with independent physical evidence, to publish null results when correlations fail to hold, and to accept that absence of direct evidence after rigorous inquiry is itself a meaningful outcome. There is a humane dimension to this restraint. If myths of gods from the Red Star are chiefly symbolic, their ubiquity still speaks to humanity's deepest anxieties: vulnerability to forces beyond control, fascination with distant brightness, and a human need to locate meaning in smallness. To read those myths only as failed history is to impoverish them. They are archives of affect, the fear of sudden calamity, the hope for supernatural patronage, the communal memory of loss that deserve interpretation on their own terms. Conversely, if, in a remote corner of the record, a material corroboration emerges, a sedimentary pocket with an unusual alloy, a meteorite whose isotopic signature maps onto an inscription, a stratigraphic layer of ash coincident with an extraordinary Martian apparition, then the world of myth and the world of rock will have met. The consequences would be transformative, but the standard of evidence must remain exacting. What, then, should the scientific agenda be in the coming years? First, an archive-sensitive approach. Compile a global inventory of myths that explicitly single out Red Star motifs, including variant phrases, place names, and ritual behaviors. Pair that database with high-precision archaeoastronomical reconstructions to identify windows in which Mars would have produced particularly bright, art, or long-lasting phenomena. Prioritize fieldwork that targets sites where mythic emphasis and preservational promise converge, lakes and craters with prolonged sediment deposition, ancient ritual centers where anomalous meteorites or iron objects have been discovered, and stratigraphic sequences known to preserve atmospheric and impact proxies. Second, a material-centric strategy. Analyze early iron and meteoritic artifacts with an eye to isotopic fingerprints that might differentiate asteroid belt material from Martian ejecta or from exotic non-solar system signatures. For artifacts where provenance is secure, the analysis must be contamination-aware and replicable across multiple labs. The standard of proof is high because the implications are large. Third, an interpretive humility. Integrate folklorists, historians, and indigenous knowledge holders as equal partners. Myths are not data mined for convenience. They are living cultural forms. Fieldwork that ignores local custodianship risks both ethical failure and scientific error. Embedding scientific inquiry and respectful collaboration enriches the hypotheses and protects the contexts. In the end, whether the repeated motif of gods from the red star is a faint, misremembered echo of meteorites and sky events, a political technology for authority, or a collection of metaphors projected onto a conspicuous celestial body, the question itself is revealing. It reveals the way human communities have always made neighborly worlds of the sky, assigning to planets the roles that help bind social life and explain danger. It reveals a species willing to make companions from light and color, and it reveals a method: test, triangulate, cross-check. The red planet will keep whatever it keeps. Myths will keep what they can. The work is to hold both archives, side-by-side, stone and story, and let the slow work of measurement and close reading determine where they overlap. Only then will the ledger close the gap between legend and faint memory, or else confirm that the red star was, all along, a brilliant mirror for what people feared and hoped to be true. Imagine a single grain of ancient Martian mud, compacted in the innermost lamina of a delta and sealed beneath layers of basalt and salt. Imagine that within that grain there is a microscopic archive, mineral fabrics, faint organics, isotope ratios that whisper of biochemical cycles, and a tiny text written in the language of atoms. The idea is simple and precise. It is also the most consequential posture that the discipline of planetary inquiry can take. The conviction that the answers to questions of enormous consequence will not arrive as shouting revelations, but as faint, patient signals encoded in narrow, protected contexts. The ledger is not a monument to spectacle, it is a palimpsest of subtlety. The story, as it has been told to this point, leaves the reader and the imagined audience at the edge of an essential ambiguity. Mars offers environments that, by terrestrial standards, were hospitable for long stretches. There are valley networks that read like weather systems, deltas that imply standing water and sediment budgets, clay minerals that point to neutral pH interactions, and pockets of organics preserved in the embrace of fine sediments. At the same time, the arithmetic of deep time, of bombardment, radiation, and changing atmospheres makes the survival of clear, macroscopic signs of intelligence unlikely. These two truths coexist, plausibility and fragility. The final chapter is a synthesis and an ethical map. It refuses both the triumphalist grand claim and the complacent dismissal. It insists on a posture of methodical possibility. First, there is a clear programmatic lesson. If the most plausible survivors of a vanished complexity are the deeply buried and chemically sequestered, then the exploration agenda must be surgical. Orbital scouts are invaluable for reconnaissance, hyperspectral mapping to identify clays, silica, and evaporites, radar sounding to map subsurface reflectors, altimetry to reveal stratigraphic relief. But the critical work is in cores, in the laminae where preservation is most likely. Drilling systems that can recover pristine, sealed sedimentary sequences and maintain contamination control are not luxuries. They are the sine qua non of decisive progress. Sample return is a scientific multiplier. A meter of mud returned to terrestrial labs yields orders of magnitude more sensitivity in isotopic and molecular assays than any rover instrument can provide. The arithmetic of detection is unforgiving. Measurements scale with instrument sensitivity, and the fingerprints of life or engineered artifacts, if they exist, are faint. Investing in the capacity to retrieve, protect, and analyze those fragile parcels is an investment in epistemic rigor. Second, the methodology must privilege convergence. No single line of evidence suffices. A morphological irregularity without chemical corroboration is ambiguous. A thin carbonaceous film without stratigraphic context is suspect. The compelling case, were one ever to be made, would be a tapestry. Morphological patterns that resist abiotic explanations, organic chemistry with complexity and structural features inconsistent, with plausible prebiotic syntheses, isotopic fractionations in carbon, sulfur, or iron that align with biological fractionation regimes, and a taphonomic story that explains how these signals were preserved. That tapestry must itself be replicable, independent laboratories, blind analyses, and multiple samples from stratigraphically separated horizons. Science here is conservative by necessity because the costs of error are not merely reputational, they reshape how humanity understands itself. Third, the ethical architecture cannot be an afterthought. If the search for ancient records leads to locales where preservation is most probable, quiet deltas, silica-rich sinters, deep aquifer exposures, then those places are fragile. The protocols of planetary protection acquire an ethical intensity when the stakes shift from mere curiosity to cultural and Historical conservation. Forward contamination threatens not only the integrity of the science, but the meaning of potential discoveries. Untested microbial communities from Earth could confound signals or, worse, irreversibly alter a site of extraordinary significance. Accordingly, the stewardship regime must be rigorous: sterile coring, sealed caches, clear chain of custody, and international agreements to protect potential sites. If there is a heritage of deep-time importance on Mars, it belongs to all of humanity and to the planet itself. Its handling must reflect that shared custodial responsibility. Fourth, the social dimension is central. Public interest in signs of past intelligence is intense and persistent. The cultural economy around images, the face, straight lines, anomalies, has shown that curiosity can be both a propellant for exploration and a distortion if unmanaged. The scientific community holds a dual obligation: to satisfy legitimate public curiosity by releasing data transparently, and to avoid stoking premature claims. That balance is operational. It requires open data practices, publication of raw telemetry and processing provenance, and the democratization of analytical tools so that independent researchers and interested publics can reprocess and test claims. But it also requires measured communication, clear statements about uncertainties, the probabilistic nature of inferences, and a multi-year timelines for definitive conclusions. Transparency is not merely a technical protocol, it is a social contract that builds trust and resists the entropic pull of rumor. Fifth, there is a philosophical humility to be embraced. The ledger of Mars, its strata, its minerals, its tenuous gases, tells a story of scale that dwarfs human history. A civilization that emerges and is erased in geologic time is a poignant possibility precisely because its erasure makes it invisible to the coarse instruments of short human epochs. This realization reframes human anxieties about permanence. The absence of an obvious Martian signature is not proof that intelligence never emerged elsewhere. It is a reminder that memory is conditional on preservation. Conversely, the discovery of a faint, corroborated signal would not annihilate human uniqueness. It would situate human intelligence within a broader narrative of possible experiments in cognition, organization, and technological expression. Either outcome prompts a similar ethical stance: humility about claims, rigor in methods, and generosity in imagining the forms that other intelligences might have taken. Sixth, the ledger invites a reorientation of imagination. Much public speculation has visualized alien mind through the idiom of the monumental carved faces, towering pyramids, ruinous cities. Deep time thinking asks for a broader imaginative grammar. Intelligence might express itself as distributed biological engineering, mineralized mats that alter sedimentary fabrics, microbial consortia that sequester metals, or biochemical innovators that restructure redox landscapes. Technology might not look like bronze and steel. It might be polymeric, biochemical, or expressed as engineered niches. The research program must therefore expand its conceptual toolkit. Materials science attuned to novel alloys and polymeric residues, geomicrobiology that recognizes deviant mineral fabrics, and statistical pattern analysis to separate biological regularity from physical fracturing. The imagination must be disciplined by the arithmetic of preservation, but free enough to recognize non-lithic legacies. Seventh, the governance and international dimension cannot be ignored. Questions of sample ownership, site protection, and the handling of potentially exceptional materials require global frameworks. No single nation should unilaterally adjudicate the fate of a find that would alter human self-understanding. International collaboration, stewardship mechanisms, and shared research facilities are necessary, not only for scientific reasons, pooling expertise and instrumentation, but for ethical reasons. The discovery of signs of past life or engineered artifacts on Mars would be a planetary event in the truest sense. Its treatment demands a planetary protocol. Eighth, there is a way to operationalize humility into concrete research priorities. Near-term, enhance orbital reconnaissance to produce ultra-high spectral discrimination over ancient deltas and hydrothermal deposits. Deploy radar sounders tuned to identify dielectric contrasts consistent with dense, metallic, or concretionary inclusions, and refine astrobiological landing site selection by combining taphonomic metrics, fine-grain size, rapid burial rates, and low oxygen matrices into quantitative scores. Medium-term, accelerate development of contamination-resistant coring systems capable of sampling at multi-meter depth and maintaining in-situ sealing. Long-term, commit to sample return capacity, targeting multiple stratigraphic horizons within a single depositional sequence. Parallel to this technological plan, invest in laboratory capacity, preserve clean room facilities, improve ultra-high sensitivity mass spectrometers for isotope ratio work, and establish international round-robin protocols for blinded analyses. Ninth, the public story must be reframed. The best narratives are those that accept curiosity and channel it into patience. The dramatization of sudden discovery should be replaced with an appreciation for slow revelation, the long reading of strata, the gradual convergence of evidence, the patient unspooling of probabilities. That is not less thrilling. The thrill in waiting for a sedimentary whisper to cohere into a chorus is the authentic exhilaration of scientific discovery. It is a discipline in trust and a cultivation of wonder that resists instant narrative closure. Finally, and perhaps most importantly, the ledger's open seam is an ethical and existential invitation. To continue the search without presumptions is to practice a kind of planetary humility, to accept that the universe may harbor experiments in life and intelligence that are brief, localized, and ephemeral, to acknowledge that absence of proof is a logical state, not a moral verdict, and to undertake the labor of discovery with patience, openness, and respect for the fragile archives we encounter. Whether the red planet ultimately yields proofs of independent life, traces of visitation, or nothing more than a richer understanding of planetary processes, the enterprise will have been worth the investment. It will be a testament to a species willing to read slowly, to test meticulously, and to accept small revelations as part of a longer conversation between worlds. The ledger remains unfinished. The page's layers of clay, silt, and salt are waiting for deeper probes, cleaner caches, and finer instruments. The silence is not a dismissal, it is a challenge. If anything, the work ahead is humbling because it reframes human desire within the vast temporal tapestries of planets. To find that Mars once hosted complex forms of organization would be to enlarge humanity's narrative. To find incontrovertible absence would be to deepen appreciation for the singularity of the biosphere Earth sustains. Either conclusion demands patience. Either conclusion will change how humans understand history. The third, and perhaps truest, possibility is that the ledger will reveal something stranger still, forms of life and memory that do not fit current categories, and that compel a rethinking of the very signals used to define life. In all these eventualities, the imperative remains the same: to read the planet's record with humility, rigor, and an openness to the deep, patient wisdom that only time can impart. The story is not finished. The last word is not yet written.